La chairmanship è tua.
Yeah. Ok, non so se mi vedete. Okay, so I was waiting 2:30, but I can start. So
we can wait. I think we better wait because people may connect at the last minute, and I see the number of people rising. So let's wait a couple of minutes.
So we can wait for a while. Okay. I don't know how many members, how many scholars we have to wait.
You can start, I think.
We can. Okay, so good afternoon to everybody. Welcome here. We have seen this morning two very interesting lessons. Now we can start the afternoon sessions. We have two topics. One is cryogenics and the second one is statistics. Both topics are really relevant for the underground physics and in general also for astroparticle physics. So the first topic, the first lecture of the afternoon is the title is Cryogenics for Noble Liquid Detectors. The cryogenics for noble liquid detectors is really important, and this is a part of the cryogenics that is involved in the underground physics. We have a part connected with liquid cryogenic noble liquids that is relevant for detectors, for instance, for neutrino physics and dark matter. And another part of cryogenics is more involved with lower temperatures, and it's mainly dedicated to the use of bolometers. This second part will be subject of another lessons that will be taken by Carlo Bucci on Wednesday afternoon. So the first lesson is cryogenics for noble liquids detector. I invite the speaker is Julian Plant. Sorry for my maybe the pronunciation of your name is not perfect.
No problem.
He's associate research scientist of Columbia University. He is a very big expert of liquid xenon. So he is expert of this liquid that is involved, for instance, in the xenon collaboration for the detector that is running in Gran Sasso. He is the expert and also head of the cryogenics and purification setup for was the head for the xenon 1 ton detector, and also now for the xenon n-ton detector. So I will give you the start. If you want, we can have a break. Otherwise, we can go straight to the end. We can decide if you want to answer the questions at the end or during the lesson.
I think we can do during the lessons, I think.
Okay.
It's easier, yeah. Because it's an overview, there's lots of different topics, so we will see how far we go.
So I invite everyone that has a question to write in the chat, and then also raise a hand, but we can have this discussion during the lesson and then at the end. So we can start. Thank you.
Hopefully you see the screen correctly. Yes?
Yes.
And you can hear me, okay. So hi everybody. So the topic, as Chiara mentioned, is cryogenics for noble liquid detectors. So what I want to say is, like, the goal, because it's such a big topic, in the sense that there's many things we could focus on. So my goal is mainly to sort of give an overview of all the relevant physical effects and all the technologies and the techniques that are employed in the design, the installation, and the operation of liquefied noble gas detectors. And there will be a bit more focus on liquid xenon detectors, because that's what I know better. But of course, we're gonna discuss many things that are applicable to many other types of detectors. So what's special about this field? I mean, it happens in other cases, obviously, but is that to really sort of understand and work in cryogenics, there's many different specialized fields that come into play in that field, such as vacuum technology, mechanical engineering, process engineering, high purity gas delivery, all these things. It's very important to sort of always be aware of all the of many different techniques and methods of all of these fields, and calculational also sometimes, and things like that. So in the lecture, I'll try to cover, it's going to be an overview, of course, but we're going to review a little bit heat transfer mechanisms and rates, how to calculate some rates. We're going to go over very, very briefly also some of the equipment that's commonly used with those with these types of cryogenic systems and apparatus. We're going to go over some of the instrumentation, how we can measure some of the properties of the cryogenic fluid that we have. And we're also going to try to do things that sometimes maybe are not discussed so much, but what are the typical operations that you do with cryogenic noble liquid detectors that are common to those detectors, and what they involve, and things like this. Then we're going to focus a little bit on the purification techniques, because it's important for these types of detectors to have very low impurity levels to be able to measure the signals that are produced in them. And if we have time, I put some special topics for dual phase TPCs that we could go over. So one thing to realize is that when you have a cryogenic fluid as a detection medium, most of the times the cryogenic fluids, they'll be it's going to be two phases that are in equilibrium, because you have a pure substance in a closed almost closed system. And unless specific precautions are taken, those cryogenic liquids always they're going to be very close to saturated conditions. So they're always going to be very close to boiling, unless like I said, something specific is done to avoid that. And this is a very different behavior than our everyday experience with liquids. Mostly when we think about liquids, we think of water in a mostly nitrogen atmosphere, and that's cryogenic liquid as a pure substance in a vacuum. In a vessel, in a pressurized vessel, behaves very, very differently. So some of these differences that I'm sure many of you know, obviously if you reduce suddenly the pressure, and if you have a liquid and the vapor above, and you reduce suddenly the pressure of the vapor, the temperature of you're gonna have flash evaporation of the liquid, and the temperature of the liquid is going to decrease to the saturation temperature at the lower pressure that you decreased, and that's not the typical behavior that you would see as much in our everyday experience. There's things that can be done. So it's possible, for example, to suppress this boiling tendency by subcooling the liquid, so bringing it further from the equilibrium curve, or to do the opposite with the vapor. So with those systems in general, it's always very good to make very small changes to change the overall state of the thermodynamic system, because otherwise it's easy to push the system in directions that what will not necessarily be easy to come back from. So the stability is one of the key things we want to think about when we operate, design those detectors. So in looking at cryogenic noble liquid detectors, we want to think, so we have a fluid who will be at the temperature that's lower than the ambient temperature. So we'll always have heat that is going into our system, and we have to remove it. So it's important to try to minimize those sources of heat, and it helps, I think, to review a little bit just what are the main heat transfer mechanisms, what do they involve exactly, and how, and because we'll see with the examples as we go along how often all specific things are done to minimize one specific type of heat transfer, and so forth. So and it's all about managing to reduce this to the lowest level, so that our system requires less energy to be kept in the lower temperature state. And so the three main forms of heat transfer is conduction, convection, and radiation, right? And conduction can be a solid, but essentially you'll have two surfaces that are at different temperatures, one being higher than the other one, and heat will flow from the higher temperature to the lower temperature you see here the rate at which this process will occur. And so this also, you have to think that it will also occur with stagnant fluids, but it will be much less than because typically the thermal conductivity, the K here, will be much lower. It's much lower for gases, for example, than for liquids. But for those fluids, there's another process that typically is much more important, and it's convection. So convection is heat transferred, from a surface. Let's say in this case that's at a hotter temperature, that's transferred to a fluid that's in movement. And here the bulk temperature of the fluid is T infinity in this one. We're going to go through some specific examples in the next slides. And radiation is of course two surfaces that are at a different temperature, so they emit radiation and but there's going to be a net heat transfer between the two surfaces. It's going to be given by the equation here, and the thing to realize here is that it has a different temperature dependence with the fourth power of the temperature difference. So if we just look at some of these and we try to think which role they play in cryogenic liquid detectors, then for conduction, one thing that we would like to do right is how do we reduce the heat transfer through conduction, so that there are many different ways. And you follow all of those at the same time. So you would evacuate gases so that you don't have gas conduction. So in a doer, for example, on the right here, the space is evacuated. So there's vacuum in the annular space here, and so you don't have gas conduction or very little of it. You would choose materials that have low thermal conductivity if you need to have something that touch something else, right? If you want to reduce that quantity here, you can reduce the thermal conductivity. You can increase the length, so that's also something that's quite common to try to, if you need something very stiff, but you don't want a lot of heat to go in, you can make it a little bit longer. You can reduce the cross section also, so the A. And this is what's happening, for example, in the neck of the dewar. You have a very thin, and that's the only place that is touching, for example, directly, right? The outside temperature, the room temperature here, and you have a very thin, let's say, stainless steel neck that goes here, and so that's minimized so that the heat transfer through conduction is not too important. And at the bottom, very often there's going to be something that prevents large side movements, but that doesn't touch necessarily all the time. So that is for conduction. For convection, like I said before, it's the transfer in energy from or to a surface due to the movement of a fluid, and typically you can separate this into different types of convection. One is called free convection, and the other one forced convection. So for free convection, it's buoyancy that's going to drive the flow. So it's density differences that are going to be making the fluid move. And in the case of forced convection, it's pressure differences that are going to make the fluid move. So on the right here, you see an example of if you have a fluid and you have two plates at different temperatures, then on the side where the plate is hotter, you're going to warm the let's say the gas that's in here. It's a closed system in this case. You're going to warm the gas. You're going to reduce its density, which makes it want to go up. And on the other side is colder. You're going to re-increase the density again. And of course, this drawing is with the gravity pointing downwards. Otherwise, it would not be exactly that pattern. So what's specific about that form of heat transfer is that it's characterized by a heat transfer coefficient, the A here. And so it's all about figuring out what is that coefficient for the specific process that we have. What is very useful is that there's heat transfer coefficient correlations that are valid for large classes of fluids, and basically they make it possible to obtain rates in problems that have a similar geometric similar geometry, but you don't need to sort of recalculate everything from or rederive everything from the beginning because you have those correlations. We're going to look at a few of them. Here in the table at the bottom, there's specific specific examples of what are the typical rates for this type of heat transfer. So for free convection, gases, you see here the heat transfer coefficient may be 2 to 25 watts per square meter per degree, whereas for liquids is much larger. But this is much lower than forced convection. And actually we'll see also forced convection as you increase it's intuitive, but as you increase the velocity of the fluid, you can also increase the heat transfer. And even greater than that is if there's phase change, like condensation heat transfer, for example. Now on to the third type that also plays a very important role for these types of detectors is radiation. And in the expression here, there's a factor that depends on the viewing area of the two surfaces that are exchanging heat via the radiation. One that depends on the emissivity of the surfaces. And so how do you go about reducing that radiative heat transfer? one possibility is to use very low emissivity surfaces. Then you'll reduce it this way. Another one is with because it's easy to see that with the fourth power of the temperature, if I have two surfaces that have a large temperature difference, it's going to be a large heat transfer. But if I put an intermediate surface that is at in between the other extremes, the other extremes, and that one is at an intermediate temperature because I have the fourth power. And if I say that the heat that I'm at equilibrium, and the heat that flows from one to the from the, let's say, the one at T2 to the intermediate one to the one, and from the intermediate one to the one at T1 is the same, then it's clear that because of the fourth power, and the difference will be less between T1 and the intermediate, and T2 and the intermediate, will have less heat transfer. So that is also a very important concept, and it's used basically everywhere. Is that there's a specific type of material that's called multi-layer insulation that has effectively many surfaces that have low emissivity and these are represented here by those radiation shields, as they're called here. And you don't want conduction between those surfaces. So you can use a material that has a low thermal conductivity plus very small point contacts between between these shields, and then you're gonna, with that arrangement, you can drastically reduce the radiation heat transfer. There are things to still sort of realize that are so if you evacuate and you don't have any more gas conduction, still. So on the plot on the right, for example, shows the thermal conductivity, the apparent thermal conductivity of multi-layer insulation as a function of the residual pressure in the vacuum space where you would have that super insulation. And you can see that it goes from few torrs, you are at essentially normal atmospheric pressure conduction, and then it decreases by 3 orders of magnitude over the course of a few decades of pressure. So you can have very low radiative heat transfer, but it requires that you can maintain that very low pressure in the vacuum space. Another element that's important is also, and it's just the plot in the middle, that if you look at the thermal conductivity also as a function of the apparent thermal conductivity of such a blanket as a function of the layer density, then there's a sort of a good if the density is too high, then you end up having too much conduction between thermal conduction between those layers, and if you don't, then you're sort of not you're taking too much space. So this is essentially what I wanted to say about these three forms of heat transfer. Now,
Sorry.
Yes.
Before you go ahead, I saw just now that there was a question, if you want to answer.
Yes, of course.
I don't know if someone wants to ask the question directly, otherwise I can read it.
Actually, I can ask. So I noticed in the I noticed that is similar to like Stephen Boltzmann law.
Yes, it is the Stefan Boltzmann law, and that's the.
And I assume the F, E, and FA factors are accounting for the fact that that law is valid for black body.
Right, exactly. The emissivity is one way of characterizing that for bodies that are not black bodies, that are gray bodies. And the other one, the A, is because you can have a very large surface that views a very small surface, and then there's going to be a factor that will enhance or not enhance the heat transfer between those two surfaces, depending how much of the total surface that's emitting is seen by the smaller surface, for example. Yeah. So this it's exactly as you said. It's essentially the difference of the energy emitted by through the Stefan-Boltzmann law. Yeah, exactly.
Okay, understood. Thanks.
So here, okay, I'm obviously not going to go through all of this, but what I wanted to introduce you to is that there's something very useful. Some of those these numbers you've heard of before, I'm sure. But essentially is the concept of what are called dimensionless groups. So in a specific problem, you always have a number of physical quantities of interest, and you can always combine them in such a way that you'll get dimensionless numbers. Okay, and so for specific problems, that these dimensionless numbers will give you an idea of the relationship between two different kinds of quantities. So one example that we could take that you've heard of before is, for example, the Reynolds number, right, which is here, and so that's the ratio of inertia and viscous forces. So that will tell you, if a fluid goes at a certain velocity, is it that inertia, is it how large is it compared to the viscous force? And so with that number, you can have an idea of whether you have a laminar type flow or you have turbulence, right? So many of those numbers are also, there's many other numbers that you can construct like this, and many of them are useful, and that's how we can calculate heat transfer rates for specific geometries, as I mentioned earlier. So another example could be the one of let's see, the Nusselt number, for example, which I think we'll see later. So this is, you see, there's the heat transfer coefficient that we were talking about before, a length scale divided by the thermal conductivity. So here's written the ratio of convection to pure conduction heat transfer. So that tells you, that number will tell you how much heat is being transported via convection as opposed to, and the larger the number is, right, as opposed to conduction. So why I introduce this is because you will see in here, and that's what I was mentioning earlier. Again, it's not to go through those things, but we can. So if you want to calculate what is, for example, the heat transfer coefficient between a flat plate at a certain temperature and a gas, like a vapor gas that is above, and in this case that has a certain velocity, you remember here that this the Nusselt number was HL over K, right? So it has embedded in it the heat transfer coefficient, and we can see here in this table, for example, this is a table of correlations. That means essentially, people have tabulated and did experiments with many different fluids, and if you have a certain dimensionless number that tells you about how much convective heat transport you have as opposed to how much conductive heat transport you have, and it's forced convection and you have flow, then you would expect that it would depend on the Reynolds number, right, which is kind of how much flow do I have, and this Prandtl number, I'm not so sure exactly how to pronounce it, I'm sorry, which is here also, and that one is the heat capacity times the viscosity divided by the thermal conductivity. So it's the ratio of the momentum and the thermal diffusivity. So with the help of those correlations, you can, for a specific problem, if you know the geometry, even if it's a completely different fluid, I'm interested, for example, I mean, we'll have a little example later on, but I'm interested in knowing how fast can I cool the wall of my stainless steel vessel with cold, xenon gas or cold liquid argon gas. Then, and if I manage to, let's say, have some flow with that cold gas, then I could use one of those correlations here, and I'll be able to know what's the heat transfer coefficient. I can use the heat transfer coefficient to calculate what's the actual heat that's transferred between the fluid and the surface, and I can calculate how fast the wall is cooling down, for example. Another important heat transfer mechanism, especially for liquid noble detectors, is the condensation heat transfer. So we have, as you said, we have a fluid that is always has heat coming into our cryostat. So we want to remove that heat, and one good way is to use condensation heat transfer, because we saw in that table it has very high. It's very large heat transfer rates per unit surface area per unit temperature difference, right? So here's a problem by actually the person that solved that problem, Nusselt. And it's the problem is the analysis of if I have a vertical surface at a certain temperature, which is below the saturation temperature of a stagnant vapor. And you have film condensation of that vapor onto the surface. And he calculated what is the rate at which heat flows from the gas into the liquid, and from the liquid into because there are several things that you need to take into account, right? There's the heat transfer that is going horizontally through the thickness of the liquid film, and then also there's gravity, so the film falls down, but you accumulate, because you have condensation horizontally or mass flow horizontally, then you'll have also a larger thickness as you go down, right, of the film, because you have liquid accumulating. And so he solved that problem, and you can see here so this delta is the film thickness, and you can get a closed form expression for what is that film thickness as a function of the distance from along the isothermal vertical surface. And you can also calculate the heat transfer coefficient, and that's useful, for example, if you want to design a condenser that will be able to extract that much heat from a gas. You need to have a large enough surface, and you need to have channels that allow all the liquid flow to be drained away, and so forth. And that's one example in which we would use something like that. Right. So this is the end of that first section on heat transfer mechanisms and heat transfer rates. And that, as I said, it was meant essentially to remind you of the different mechanisms that exist, and also what are as a cryogenist, what are the things that you try to keep in your mind as you analyze the problems, and you look at, as we look also at the equipment and as other things, what are the specific concepts we should keep in mind. So in this section, about the equipment, obviously, again, the equipment can be, we could spend weeks going over what exists, what is useful, and so forth. But what I thought I could do is basically a brief look at some of the equipment that's commonly used and also not so commonly used, but in cryogenic liquefied noble gas detectors, and you'll see throughout what the concepts that we discussed before, and how they come into play, and what are the design choices that people have made. So we're gonna go very, very briefly over each type of equipment that's written here, but cryostats, some cooling apparatus, how do you transfer cryogenic fluids to minimize heat input into the fluid, valves, and pumps. The other thing to realize is, again, this is with always keeping in mind that we want to have a detector that has a very low amount of impurities, and so the cleanliness, is important. The leak rates of impurities into our equipment is important also. So so cryostats, that's the, to say just one very brief description, is where you keep the cryogenic liquid cold, right? And here, for example, is a drawing of the Xenon 1-ton cryostat vessel, which is in the center of the water shield. And so this internal vessel that you see here is the one that is filled with liquid xenon up to some certain height, and the time projection chamber, which is really sort of the heart of the detector, is sort of bathing in the liquid, right? And the external vessel that you see here is at essentially room temperature, and the space in between is evacuated, and the inner vessel is covered with a form of insulation. So it's covered with the super insulation that we discussed before, the multiple layers of low emissivity foils. And so what is common that you would see in every cryostat that you look at is sort of the things that we discussed before. You want to minimize the heat that goes into the cryogenic fluid, so you would like to have some form of insulation. The lower the heat transfer, the better. So vacuum insulation, and once you have vacuum and you want to reduce radiative heat transfer, then you would use the multi-layer insulation. You can also use passive insulation, and depends on the specific constraints of your detector. The other thing that's common to all cryostats is you have to manage thermal contractions, because you want to have a cryogenic fluid in a vessel, but with the large temperature difference that it will go through, you'll have thermal contractions of the metals that you use and so forth. So you need to take that into account so things don't break. So what you can see in the drawing on the right, for example, that goes along this way, is you can see the sort of the pointy things here. So that's to minimize the conductive heat transport, because you need to support this tube so this tube essentially brings a liquid, so you can take out liquid to purify it from the cryostat. You return liquid to keep the liquid level. There's signal cables to multiply tubes and so forth. But so all of that, all those service lines need to be sort of suspended and they have to be supported in some way. So if you use point contact, then you'll minimize that heat transfer. The other thing that you see is that, well, it's not so clear in that drawing, but essentially there's some axial movement, some axial freedom in the horizontal part, and then so that even if it contracts, you won't have large thermal stresses into the materials. In the case of low background experiments, there's also other constraints. One is so you want a low background experiment, which means you want a low radioactivity burden, let's call it. So you want to minimize the mass of the cryostat, which means that the pressure resistance of that vessel is going to be diminished, right? So it's an interplay between what are the conditions at which you want to operate the detector, and also what are the sort of the sensitivity you want to reach with your experiment, if it depends on a specific maximum amount of radiation that's emitted by the materials that are in close proximity to the detector. Then for very large detectors, there's even, there's bigger challenges. And here I put the picture of the Protodune cryostat. If it's a very large, cryogenic cryostat, you will have to deal with large thermal contractions, right? So you'll have much greater total displacements, and sometimes it will be very impractical to manage to insulate it with vacuum insulation, because it will be, you would need, for example, a wall that's too thick, or it would be very expensive just to construct to have such a large surface with vacuum insulation. So this concludes just a brief discussion I wanted to make about cryostats. So another piece of equipment that is important is what you use to remove the heat that flows into the cryogenic fluid in the cryostat, right? So there are many different strategies, and there are many different technologies and so forth. So the more common ones are to use cryocoolers, refrigerators, or to use a fluid that you can use its latent heat to cool your detector, or to extract heat from the cryogenic fluid of your detector. So here I gave examples in the case of the experiment that I work in Xenon. We use pulse tube refrigerators, but also GM refrigerators, and we also use liquid nitrogen cooling for different for the storage vessels that we have, and for also for a new system that we built for the new Anton detector cryogenic purification system that uses a liquid nitrogen, liquid xenon heat exchanger. And there are many other experiments that use the same type, that use also liquid nitrogen cooling in different forms. I mean, with specifics that depends on exactly how the heat is extracted from the cryogenic fluid of the liquefied noble gas detector. Now, if we want to transfer that fluid from one place to another within our experiment, we need to do so without having too much heat going into the fluid, right? So one specific type of equipment that's used for that is vacuum jacketed piping or super insulated vacuum insulated transfer lines. So you have a drawing on the right of what this looks like. It's very similar to and you'll recognize many of the features that we discussed before, right? So to have a low conductive heat flow, so the fluid would circulate in the central tube and would be very cold. The outside tube would be at room temperature, and it's such that we can evacuate the space in between, right, to reduce the gas conduction. And it also would be polished to have a sort of low emissivity, so that you would even gain a little bit on that, well, not a little bit, but you would gain also on that, from that. And to have low conducting heat flow, the supports you would use, typically it's I wrote here G10 is a plastic that has a lower thermal conductivity than metals. And you see again the strategy of the point contact. So here's a simple, commercial product. So you want something that's easy to manufacture also. So that's why it's a square and just a hole inside it, and you can slide the tube in, and it will keep the cold tube in the center but have a small thermal contact to the outside. To reduce the convective heat flow, again, we said the vacuum insulation also, and you can even put getter pumps to reduce even more the pressure, to keep the low pressure as long as possible if you are not actively pumping that space. And to reduce the radiative heat flow, you would put super insulation or multi-layer insulation around the tube. And you can see, for example, here a bellows, so kind of an accordion style stainless steel piece that allows for axial movements, so that you can, the tube here on the left can contract if the tube on the right, for example, stays fixed, or the other way around, and you won't have any large thermal stress that could break the tube, because this will take the slack. What's important to realize is that, so as we said before, right, the cryogenic fluid is always sort of on the point of boiling. So if you subcool it, still, if you let heat flow into it, its temperature will slowly, rise. And so when you size tubes that you want that carry a cryogenic fluid, it's important to know what is the mass flow that you will have through the tube in liquid form, and you have to choose appropriately the diameter of that internal tube, because if it's too small, for example, it's possible that you will not be able. So if you put the cryogenic fluid and you have a warm tube, it will vaporize, right? Because it's a lot of, in that case, boiling heat transfer. So you have a lot of gas that's generated. That gas needs to escape, but the tube has a pressure loss itself to let that gas come out. So it's possible that the tube is so small that you cannot cool it down with the cryogenic fluid, because the gas that gets generated to cool it down cannot even escape to continue that process of cool down. And then at the other extreme is that you could if the velocity of the fluid in the tube is very low, then you'll have too much heat that goes into the fluid, and it will become saturated instead of being subcooled. So then you'll have bubbles, and then two-phase flow, meaning you'll have a mixture of gas and liquid in the tube, and this can also create problems depending on exactly what is the goal of transferring the fluid. Valves is another important. We have somewhere to store the liquid. We have a means of transferring it from one place to another, but sometimes you want to choose whether you transfer it or not. So with valves you can do that. So what are the typical requirements for valves for cryogenic noble liquid detectors? Is first you want the compatibility with the high purity fluid, right? Because you need to keep that to be able to operate your detectors. You would like electropolished surfaces, or very low surface, jaggedness, surface roughness. Sorry, you don't want any lubricants that to be used that could go into your cryogenic fluid, and that's the target of your detector. You want low heat flux, right? So you don't want a lot of heat to flow in your liquid. We talked about that a lot already. You also don't want to lose the fluid. So you want a good sealing mechanism, and you also don't want impurities to come in your fluid. And so one specific type is with a bellows sealed valve, so that you have a metal essentially surface that isolates the outside from the inside of your system. You would like reliable low temperature operation, right? You want that it just works, and high flow coefficient is just so that you don't have large pressure drops along your system, so you can transfer the fluid without losing the too much pressure along the path of the. So what you would also like, right? You would like the valve to have a low heat capacity, so that it doesn't take too much cryogenic fluid to cool down the cold part of the valve. And you also probably would like to be able to service the valve even though it will be installed in the vacuum jacketed line. So in the picture on the right, all the features many of the features that we saw that I listed on the left, you can see how they are. So this would be the tube where the cold liquid or cold gas, but typically would be cold liquid, flows. And So the valve blocks, the plug of the valve blocks the seat of the valve here and prevents the fluid to go. But when you, let's in this one is a manual valve. So when you turn the handle here, this, you see that it's the stem is fixed and is going up, and it will go up and will compress the bellows here. So the bellows is welded to the inside and then welded or you know, with a specific type of seal to the outside, so that there's a continuous metal surface that isolates the inside of the valve to the outside. Then, so that's for the, you know, the external leak, right? The low heat influx, you see that there's a very thin wall. So this is at room temperature, this part here that is outside. And you see that from the room temperature part that goes directly and touches with a metal surface, goes and touch the fluid at some point, but it's a very thin, both the wall of the inside part and also the shaft, instead of being a straight, you know, rod that goes down to the plug, you see that there's this, so there's a reduced cross section. So increase the length, as we discussed before, reduce the cross section of the metal to all of it to reduce thermal conduction from the so because the room temperature outside could of course mean that there's a lot of heat that flows in, and then when your valve would have a lot of ice outside and things like that if the design was not a good design. Now another so now we discussed a few things, but if you want to have a source of pressure difference to move the cryogenic fluid from your cryostat to your storage, or from your storage to somewhere else, so you can use the pressure, like static pressure differences, but you can also use pumps that will move the fluid, and there's such equipment to move cryogenic fluids, and that the specific type that I'm showing here is one that's been used by a number of experiments that are listed here. There's a company that manufactures this specialized equipment that has the characteristics that I listed here. So again, you would like to have a high purity fluid compatibility, right? So that specific pump solves that problem by having a hermetically sealed pump volume and magnetic coupling to the shaft, so that you can have a completely sealed volume where the cryogenic fluid is. A stainless steel construction again for the high purity. The low heat influx with, you know, a very thin wall, again from the room temperature part to the cold part where the liquid would go here. There's a sort of helical, like a screw that's called the inducer to help the cryogenic liquid go where the impeller is, and then the higher pressure outlet is here. So that's the cold part. And to prevent this heat influx, you also have those anti-convection baffles. So we saw that if you have, you know, warm surfaces, cold surfaces, you can have convective heat transfer in enclosed spaces. Then, if you put you know, plates like this, they will prevent that convective heat transfer or reduce it. And vacuum housing, again, removable rotating assembly. So many different parameters and configuration that help having a pump that solves the requirements that you have to use. So this is an example of a system that we use in our experiment for the purification of liquid xenon. And if here, okay, you can see many cryogenic valves with the vacuum insulation outside. It's hard to see, but there are also the cryogenic liquid pumps here. All of it is with vacuum jacketed piping, so that there's a small heat transfer to the fluid. And And then that brings us to the next section, is the instrumentation. How do we go about measuring properties of our cryogenic fluid? So of course, it's important to be able to measure those properties and to not so for example, temperature, the pressure, the flow, the quality, so the vapor fraction of the liquid, if it's not all liquid, the liquid level, you need to be able to measure all those things to be able to operate your liquefied noble gas detector. So but measuring those properties at cryogenic temperatures, sometimes it can bring about subtle challenges that we're not used to. So here I just wrote a few little things, but if it's possible, it's good to use conventional instrumentation instead of putting, there's complication in having instrumentation inside the external wall of the cryostat and all of this. For the sensors that need to be there, then it's good to put some redundancy so that you don't have if you lose one sensor, you can still do measure what is needed. So the robustness of the sensor and the mounting is important. So to measure temperature, so very often you need to measure, and specifically with cryogenic liquid noble detectors, one usually needs to measure the temperature of gases, of liquids, and also of surfaces, right? And if you want to have an optimal performance with the cryogenic temperature sensor, you'll need to consider these three aspects, which will determine how well you'll be able to measure, is how you mount the sensor, right? So you have to, if there's any form of current that goes into the sensor and it heats, it needs to be able to dissipate that heat so that you can measure the temperature of the fluid and not the temperature of how much you're heating your own sensor. You have to minimize the thermal contact resistance of the sensor with what you want to measure, all right? And you also have to match to some degree sometimes the thermal expansion coefficient so that you don't, when you cool down the sensor plus thing you want to measure the temperature of, the contact doesn't break because they have two dissimilar thermal expansion coefficients. The joining of the sensor and the electrical cables is also very important, and it can give rise to differences in the offsets and so forth. Another important part is that the wires will be connected on one side at room temperature and on the other side to the cold sensor. So you need to have some form of thermal anchoring of the wires. So basically wind the wires or have them exchange heat with a cold surface that's in between the external feed through for the external feed through and the sensor. There are, of course, there are many types of sensors also to choose from. Here's just a table with many different characteristics of those sensors. Usually, I mean, the things to think about is what is the range of temperatures you want to measure, what's the lowest temperature you want to measure, the reproducibility, right? The response time sometimes is important also. It can depend on the specific geometry of the sensor also. For liquid noble gas detectors, a very common choice is platinum resistance temperature detectors. So this is a resistance that will change as the temperature change, and by knowing that curve of the change of the resistance with temperature, then you can, if you measure the voltage drop across the resistance, you can know what's the resistance and you can know what's the temperature. So here are some examples of those that are commonly used. You can also, so those can be immersed in a fluid, for example, but you can also have them in a package such that they can be bolted onto a surface. And they, another thing that we talked about a few times before, right, is the compatibility with the high purity fluid. So or high vacuum environment also is the same. So that's also a consideration when you want to purchase some of those sensors. to measure the pressure, one trick that can be done, which is what's shown on the right here, is to essentially you use a room temperature. So you want to measure the pressure of a cold cryogenic fluid, but you don't want necessarily to have to buy a sensor that can withstand that very cold temperature and put the sensor right next to the fluid. So you can use the increased distance for thermal decoupling, right? And here in that little schematic I put, you use something that so the pressure will be the same everywhere, but you take a protrusion, and because it's vertical and because you'll have a thermal gradient here, and once the gas is hot above and the gas is cold below, and you have the vertical temperature gradient, you won't have much heat transport, convective heat transport, because it's a stable situation, and you can measure the pressure that way. There's many types of commercial transducers for high purity gases that are adequate and with acceptable accuracy and the features that we want. In the case of cryogenic liquids, you would use a sensing tube, right? So a tube that goes to where the cryogenic liquid is, and you can measure the temperature also with that trick. So here, for example, I show for the vacuum transfer, the fluid transfer line that we were seeing earlier. If you wanted to measure the pressure along that tube before or after a pump or something like that, right? So here's the external room temperature part. You have a tube that goes in the liquid, and here is closed. The pressure transducer is a closed volume, right? So the liquid would go a little bit here, but it would vaporize, and then the stable liquid configuration would be something like this, where if the liquid goes a little bit higher because there's a pressure fluctuation, will compress a bit the gas here, but then it would slowly, this part is uninsulated, so it would slowly absorb heat, and then the liquid would sort of vaporize or retreat, and with the increased pressure. So these are ways to use a room temperature pressure transducer to measure the pressure of a cryogenic fluid. Right. To measure the flow, there's also many different techniques. One is a Venturi, it's called. Another one is a Coriolis flow meter, and there's other types also. A turbine, which is literally like a little turbine that turns, and you measure the speed at which it turns. Another one which is with the pressure difference orifice plate. Sometimes it's simpler to use, something to measure the gas flow, the gas, than to do it with the cryogenic liquid. So that's also possible if you use a heat exchanger, and we'll see that a bit later. What you have to realize is that all of these flow meters, they're very sensitive if you have two-phase flow conditions. If it's not just a liquid, 100% liquid, it will the pressure difference will be different, and then you'll interpret a different velocity for the fluid. And again, for these types, you can use room temperature differential pressure transducers to measure the pressure drop. So here are some examples. You have the fluid going here. Again, the vacuum insulation here. The fluid goes here. In a venturi, there's a restriction, which means that the pressure will be a little bit. There'll be a pressure drop, and you can relate the volumetric flow of the liquid as a function of that pressure drop. But you can use a differential pressure transducer that's at room temperature and connected in the ways that we saw before. Another one which is cool is the Coriolis flow meter, and this is using the Coriolis fictitious force. Essentially, the cryogenic fluid goes into sort of not a loop, but kind of a bend, and in some of them it goes in two, and you induce some oscillation. So that oscillation is the sort of the accelerating frame of reference in which the Coriolis force would appear. And so if you remember this, that it goes as the angle vector product with the axis of rotation cross the velocity of the fluid, then what will happen is that when you don't have flow and you make those tubes oscillate back and forth, they'll be in phase. But when you have flow, there'll be a twist, because on one way the fluid goes in this direction, and the other way goes in the opposite direction, and that will then you'll have the cross product is going to be the other way. So it puts some bending moment in the tube, so it makes it twist, and the phase shift between these twists can tell you. So it's a clever trick to measure the mass flow rate. So the mass flow rate is going to be proportional to that shift, and you can even measure the density, because this is like it's like a spring, so the mass is different, the frequency will be different. So you can measure also the density, as opposed to that specific device can only measure you'll only measure the pressure difference, and you'll be able to relate that knowing the conditions of your fluid, but not necessarily, you won't be able to know what is the density with the. So if you want to know what is the density, what's the fraction of a gas that is in your cryogenic fluid, you like I said, they're often near saturated conditions, right? So if you have a little bit of a pressure drop, you'll have vapor that's generated. So maybe you want to know what is the fraction of vapor that you have in your fluid. I mean, it always depends what is the specific process. But so the capacitance measurement is a common technique for that to measure the vapor quality, or the vapor fraction, sorry. So basically you set up a cylindrical capacitor. So that's the inner rod, the external rod here, and the external cylinder, the inner rod. And because the dielectric constant of the gas is going to be different than the dielectric constant of the liquid, then the capacitance that you measure for that arrangement will depend on the average dielectric constant of the two. And so you can see that if you plug this into this equation here, if you measure the capacitance, you can invert that equation to extract what is the vapor fraction, the fraction of gas that you have in that volume. And you can also use it to measure the density. So you can use that to measure the density coupled with, for example, the venturi that we had before, and then that would give you what is the mass flow rate instead of just being the velocity. Yeah. To measure the level, there's also various techniques. You can use the hydrostatic pressure, again, the capacitance, electrical resistance. So the most commonly used one are the hydrostatic and the capacitance methods, and so the capacitance one has a greater precision. That electrical resistance one can be used to kind of as a switch to know if the level has reached this spot. For example, and that's basically because if you have a little bit of current going through that resistor, it will heat more if it's in the gas, because the convective heat transfer will not be as high, so the gas won't be able to remove as much heat from the sensor, so this temperature will be higher, whereas it's in the liquid, it'll be lower. So that's one way of sort of knowing if the level crossed a specific point in your detector. You can use also the hydrostatic pressure to measure the level, right? So you put a sensing tube at the bottom here, so that gives you the pressure at including the hydrostatic pressure of the liquid and of the gas, and you measure the difference between that pressure and the one at the top of the detector. Yeah. And you can also do capacitance level measurement by having the same configuration as we discussed before with the cylindrical capacitor, but placed vertically. cryogenic fluid, and so the capacitance is going to depend on the height of the liquid in here. So you can invert this and figure out what's the height of liquid in your detector. So now I would move to the typical operations that you would do with cryogenic liquid detectors. So we'll go kind of quickly also, because I see the time is flying. The one typical operation is the evacuation. So kind of try to reduce the quantity of impurities that we will mix with the cryogenic liquid when you fill. Cooling down to prepare the vessel before putting the fluid. Filling, which is actually transferring the liquid into that detector. And the data acquisition and the continuous purification, which is the state where the detector spends most of its life. That's what we built it for, essentially. The recuperation, which is say the gradual transfer of the cryogenic liquid from the detector back to the storage. So there's some of these things that, I mean, it's not necessarily for all detectors. If you have a very expensive fluid, probably you absolutely want to recuperate it. If it's a very small detector and it's not an expensive cryogenic fluid, maybe you just vent it in the air. If it's a very large detector, then you probably can't do that. So evacuation, as I said, the main purpose of that operation is to reduce the quantity of impurities that you will mix with your pure fluid when you put it in your detector. So often you do this with turbomolecular pumps and dry vacuum pumps. It's not always possible to have that step because maybe the very large cryostat cannot withstand the external pressure and evacuate it. And you can use dilution to reduce the quantity of impurities that you'll mix. You can calculate, for example, what is the vacuum level that you would require before you can fill that detector, and that often is dictated by the impurities that are going to be continuously released. So here I just wrote a simple kind of estimate of if I wanted to have 1 millisecond electron lifetime in a 10-ton liquid xenon detector, what would that put as a constraint for the vacuum, for the outgassing rate? So the electronegative desorption rate of impurities that I can tolerate, and also what's the vacuum level to have that. So you don't have to go through this, but it's basically straightforward that you can calculate if you want to have that concentration of electronegative impurities in that detector. You can calculate how much, depending how fast you're purifying that detector. You can calculate how much of that electronegative impurity can be released per unit time, and then assume some factor between the release rate, the desorption rate at the cold temperature versus at the room temperature when you are evacuating your detector, and then estimate the vacuum level requirement, knowing the pumping speed of your apparatus. The next thing that you would do after that is to cool down the detector. So that's to reduce the thermal gradients in the detector components, right? While you're filling with the liquid later on. If you have a warm, fragile detector and you suddenly immerse it in a cryogenic liquid, you can be all sorts of boiling and all sorts of contractions that might, thermal contractions that might not be symmetric, that might end up breaking things. So often the largest thermal mass, so the thing that you have to really cool down, is the cryostat, but you have something fragile inside. So that fragile thing is probably what constrains the cool down rate. And so with careful design, you can sometimes cool down the inner structure and fill at the same time. So that is if it's okay, but you have to be careful. But in general, you'll sort of try to do this and reduce the temperature before, and then you can use the fact that, so if you just want to use cold gas to cool down the cryostat, as we saw before, that heat transfer coefficient not being very high, it's going to be more efficient to condense the gas, have it transported as a liquid to your surface, and then evaporate. Then the heat transfer rate here is going to be much higher, and the heat transfer rate here the heat transfer goes in that direction. Of course, the heat flows from the warm cryostat to the cold refrigerator here, for example. And it's going to be more efficient to do this. If you want to do it slowly, you can limit that condensation rate to limit the rate at which you cooled the detector. That is so that's one example where you can use the correlations that we looked at before, right? So if I take one example here, I have a very small wires, right, 100 micrometer diameter, but I have a big support ring for those wires, 2 centimeter, and it has a 1.5 meter diameter. And I want to know how fast does the wire cool down compared to that ring. So I can use that correlation for a cylinder that it's inside a gas at a lower temperature, for example. And then I can calculate the heat transfer coefficient, and then I can know, okay, what's the cooling time constant for my wire that has a certain mass, certain heat capacity in a certain area, and for the ring. And you would see that with those numbers, you get something like 17 seconds to. So if you have a thin wire of that diameter and you immerse it in a cold gas, the relaxation time, the cooling time is going to be about 17 seconds for that wire, and about an hour for the frame. So you'd have to, impose a slow cool down rate so that you can maintain an acceptable temperature gradient between your wires and your frame, so that they don't break. The filling itself then it can be done in a number of ways. You can very often it's done in dynamic equilibrium at approximately constant pressure. I mean, when you have an expensive fluid, you don't want to vent the excess pressure, so that's why you basically try to adjust the condensation rate as you're filling into the vessel with the available cooling power that you have, so that the whole system stays at constant pressure. You can do that in the gaseous phase, right? So then you'll be limited by what's the cooling power of your refrigerator, your cooling apparatus. And then you can purify that gas before putting it in the detector with traditional gas purifiers. You can also fill the cryogenic liquid directly, and that will potentially give you faster filling rate for limited cooling power, because you'll have already the liquid cold. Then of course cool down is probably a requirement, because the I'm sorry, I'm getting a phone call, but if you don't cool down, then you'll immerse with the cryogenic fluid your detector directly, and then it's more likely, as we said before, that it breaks. In the case of xenon 1 ton and ton, we use heat exchangers that allow us to still purify the gas while we fill in this mode, and that's what's shown in this slide here. So here on the left is the storage vessel that has the cryogenic fluid, and here's a pump, here's the purifier that you use to purify the gas, and here's a heat exchanger, and here's your detector that you want to fill. So you take the cryogenic liquid here, you use the pump to draw it into the heat exchanger. The heat from the purified gas that comes back to the heat exchanger is enough to vaporize that liquid, and it gets purified, comes back here, and then is recondensed by the cold liquid that's in the other direction that goes out, and so in that way you can sort of fill faster than would be the cooling power that you have on that side. Okay, for the data acquisition and the continuous purification period is, like I said before, it's the state that the detector will spend most of its life, right? Is the reason why you built the detector. So what are the requirements on your cooling system for that? Is to maintain this thermodynamic condition as stable as possible, to extract heat that's constantly flowing in, right? To keep the temperature, the pressure, and the liquid level constant. You want to have equipment redundancy for continuous operation, and you want to be resilient to unexpected equipment failure and be able to maintain and still keep running, and resilience also to loss of electrical power. Very often, continuous purification is required to reach the required purity, because you have continuous impurities that are being released in the liquid. Right here I said that the continuous removal of radioactive impurities, for example, radon, that can also play. It can also be an important element that you have to take care of. That we will see a little bit about this in the next section. And the recuperation is the transfer, that you take the cryogenic fluid from the detector that you were operating, and then you transfer it to storage. The gradual transfer. So there might be multiple reasons why you wanna do that, right? Is maybe you want to maintain your detector, or you want to upgrade it, or you have severely limited access, or you want to decommission the experiment. And again, you can do that in the gaseous phase or in the liquid phase. And then here I show just a certain number of storage vessels that you could have. You could have high pressure cylinders, liquid gas storage. This is the one that we have for xenon 1 ton, and this is for also in the xenon n ton. Now, the purification techniques that you can use to clean the liquid of that detector, there's sort of broad subdivision, which is the batch purification. You want to remove everything so that it's clean and you can fill the detector. And there's also the continuous purification for the removal of impurities that are constantly released. On top of that, you can further divide and into two categories. Let's say one would be the electronegative impurities, so those that would reduce the size of the signals that you want to measure with the detector, and like such as the scintillation light or the ionization signal. So for that, you want to choose materials that will minimize this desorption rate of those impurities, and you also I'm sorry. You also want to be able to do that, it's good to measure the material properties ahead of time and to model the expected amounts that they will release. For radioactivity, for radioactive impurities, for cryogenic liquid detectors, very often, in the case of xenon, a big source of background potentially for large detectors is radon 222, but also krypton-85, and these are two, of course, noble gases themselves. And so for radon, you can minimize it with different techniques. You can sort of prevent it from reaching the target. You can remove it before it decays in the target, so that you don't have it doesn't influence it doesn't decay in your detector. And then contribute to background. Krypton itself will not be produced continuously like radon will, but it can still sort of outgas or leak in. So maybe you want to continuously purify it. For gas phase purification, the traditional, let's say between quotes, way of doing that is at low speed. It can be just directly taking the gas phase and purifying it and putting it. Taking the liquid, vaporizing it, and putting it back in the detector. If you want to go at higher speed, you'll probably want to use, heat exchangers to keep not have too much heat going in your detector with that purification loop. The features that you would like to have is a large mass flow rate, a continuous operation, pump maintenance while the detector is full so that you can continuously take data. Downtime from purifier replacement is another thing that you would like to have multiple purifiers so you can do both at the same time. And you also want those components to have a small contribution to radioactive impurities. You can use commercial gas purifiers for the flow rates that are required for these detectors, and then they will remove the typical permanent gases and the electronegative ones. And in the case of xenon, one of the gas pump technologies that was developed was based on another experiment, EXO, is with a magnetically coupled piston pump that it can be built with very clean materials and can have the volumetric flow rates that are needed for the purification. This works up to a point with much larger detector, then it becomes more useful to use a cryogenic liquid pump and have the large mass flow rate that pump can give you, and then just you let the cryogenic liquid flow through a vessel that has some form of sorbents that will remove the impurities that you want to remove. And there are high performance sorbents that exist that you can use to remove the electronegative impurities. Very often they have high radon emanation rates, so that kind of makes it a little bit difficult to because it means that you're having another problem. So for low background experiments, you need both something that has a high capacity to remove oxygen, for example, to maintain your charge signal and have a high electron lifetime, and also have a low radon emanation rate per unit absorption speed for the electronegative impurity. So this was implemented in a number of experiments. For us in xenon, it was done for xenon N-ton, so the detector that's currently running, and with that system we could achieve the purity levels that we wanted.
May I ask you a question?
Yes, of course.
Also,
yes.
because you can breathe for a while. That's a question, because sometimes these TPC are just for charge, but most of them uses also scintillation light.
Right.
And scintillation light, also nitrogen is a problem, and if you have a leak from atmosphere, you have an income of nitrogen. I see in your slides that you speak about nitrogen purification only in gas phase. Can you comment a little bit more on this?
It's I think it would be so. Okay, so the difficulty in removing impurities at low temperatures is just essentially just the the Boltzmann factor of the on top of the reaction. So you'll very often have much lower rates because the temperature is much lower. So you need something that's already very reactive. But there are materials that will that still will be able to probably remove nitrogen. I don't know specifically in the case of xenon. We are not so much. I know argon is the nitrogen is a problem for the scintillation light. I guess and then with xenon the nitrogen would tend to, remain in the gas phase of the detector. So that's why for us, it's easy to have a very fast cycle in the gas phase of the detector and remove nitrogen. So it's not as required to have a fast. Most of the biggest impurity that is problematic for the scintillation light in xenon is water, and that is, let's say, easier to purify for. So yeah, so I think there must be sorbents that can remove nitrogen even at liquid argon temperature with the cryogenic liquid purification. Okay. But it would be you would need sort of dedicated tests to verify which ones work, which ones don't work.
Okay, thank you.
Unfortunately, it's a very xenon-centric experience, that of the cryogenic purification.
Okay.
You know? Yes,
It's
yes.
okay.
One of the last topic I wanted to discuss was another way of removing impurities from a cryogenic fluid, which is if the impurity has a different boiling point, then you can use cryogenic distillation to be able to separate your target material and remove those impurities. So in the case of different xenon experiments, XMASS xenon, that was used successfully to remove and reduce to very low levels of krypton 85. And it can also be used to continuously remove. So as I was saying earlier, the krypton will also sort of tend to be more because of the ratio of the boiling points, will tend to be more in the gas phase than in the liquid phase. So at least the molar fraction in the gas phase will be higher. So it's possible to extract the gas, pass it through a cryogenic distillation column to remove the krypton and have krypton-free xenon gas, and put this back in the gas phase of the detector, and do that fast enough that you sort of drive a disequilibrium between the liquid and the gas volume, and it's possible to remove the krypton of the liquid. There's another, okay, for our new experiment, there's also a similar system that's used to remove radon. What is new about it is that with the cryogenic liquid pump that allows a time scale to extract, to remove the liquid and circulate the liquid from the liquid volume faster than the decay time of radon. Then if you have another way of removing the radon from your fluid, then you can sort of remove the radon before it decays in your detector, and just by the virtue of the fast circulation rate. And then your apparatus to remove the radon. So in our case, it's also a radon distillation, is a cryogenic distillation column also for that. So it's possible to get a even greater enhancement, reduction in the background from that specific components. In the case of DarkSide 20K, there's a very large distillation column that's going to be used to separate argon 39 from argon 40, and will be used in a batch purification mode, and not a continuous mode as I was describing earlier. But so these are all ways in which you can reach very low levels of contamination with radioactive impurities in cryogenic noble gas detectors. So I see that it's...
You have still 15 minutes.
Still 15 minutes.
You want?
Yeah,
no
so
way.
we can, I guess we could just...
Yes.
I can just explain that, maybe one topic, and then if people have questions, we could do that. So of course, having a dual phase TPC means there are other challenges to operate those detectors. One of them is to have so the place in the detector where the signal is the charge signal is converted to a light signal that can be measured with PMTs is called typically the proportional region, and you want to have a stable gain for that amplification mechanism, and you also want to be able to choose what is that amplification. So that means you, in general, right, you have a cryogenic fluid, and you want to have its level be exactly and very precisely a fixed position. You also don't want fluctuations from pressure or level. So in that specific case, how it can be, there are different ways it can be done, but it kind of brings together a bunch of the concepts that we discussed, and also is part of it is a little bit interesting, and it's funny how these liquids behave, these cryogenic fluids behave. So in the case, so I want so let's say you see the dotted lines here are the electrodes, and we want to have the level be at a very specific position here. So one way of achieving that is with something that's called a diving bell. So it's a closed volume, like I don't know when, but back in the day where they would just lower this in the bottom of I don't know, the ocean or or a lake, and it would be possible to, there would be air in that bell, and people could look at the bottom of the seafloor, I guess. But in this specific case, you can, if you don't do anything and it's a completely closed volume, the cryogenic fluid will likely, you know, evaporate and make an atmosphere at the pressure that corresponds to the corresponding pressure here. So you'd have just an empty volume, but you couldn't choose what is its height, right? So to be able to choose which the height that you want to have, you can put a flexible piece here and have an overflow tube that goes on the side. And if you have a mechanical motion feed through, as it's called, but something that allows you to translate up and down a shaft that's connected to the end of that tube, then if you have a mass flow rate of gas in that volume, if that mass flow rate is larger than, so what will happen, right? If I have this is a pure, I have just one, basically just one substance in here, that's like xenon in this case, or argon, then here I'll have a cold surface to some degree, and I have a very large surface. This gas is probably some degree warm, and so I'll have some condensation of that gas onto the sides here and onto the large surface. So if the mass flow is larger than that, than those conditions, then I can have some gas that escapes here, and roughly the level will be at the height of that overflow tube, and I can adjust up and down that. So that's one trick. What's funny about it is that if you, as I was saying earlier, is if you don't have enough flow rate, it will still work. Just you will be able to maintain some type of height difference between the level outside and the level inside. There won't be any gas. Just the liquid, the gas that comes in will condense and maintain the level at a certain height. So it's kind of, is not a very common, like I said, like I mentioned at the beginning, everyday experience that you can pump something, push a fluid with a pump somewhere, and it just condenses, and you have sort of a dynamic static situation. Another way to do the same, to solve the same problem, is with sort of an overflow, so kind of a little fountain of your cryogenic liquid would go in here, and then here you can extract the liquid from that volume, right? So you have continuous stream falling and replenishing this. You pull this out, and if you want to adjust the height, you can move up and down the end of that tube with the bellows here. So that is the end of basically what I had prepared. I think we are not, or very close to the end. Yeah. So I hope that yeah, we covered many things. I spoke continuously for a long period. I hope that you know, this introduction and this overview can kind of help you maybe as a guide to further explore, or at least be interested in the behaviors of and all of the equipment, the technology, and the physics that are involved with the design, the operation, and of those types of detectors. Thank you.
Thank you very much. Fantastic talk, because it was very interesting, extensive and detailed. I think you were able to summarize everything is needed in cryogenics technology in less than 2 hours. So it's incredible. Congratulations.
Thank you.
I don't know if someone has some question. There is also a session for questions later, but in case there are some few questions now, we can also try to answer. And let's see. Yes, there are 2 questions. I see some hands. Walter?
So first I join in congratulating with Guillaume for the fantastic talk that I also like very much. And ask you to upload the slides. To send me the link for uploading the slides.
Absolutely, yes.
Then I would like to understand why I noticed that the experiment to keep the detector cooled, they move essentially in growing size from the cryocooler method to the cooling with the liquid nitrogen. And I was wondering why this happened.
Right. I think, yeah, I don't know. I think maybe it's a little bit because of the simplicity of the liquid nitrogen supply tank instead of the secondary cooling loop like Icarus, for example, had, right? With then a refrigerator to recondense your nitrogen. I think it's maybe just because of the I don't know exactly, but I think it might be just because, yeah, maybe people find it simpler to just have a large volume of liquid nitrogen that gets refilled by by trucks than to have the dynamic system with the refrigerator that recondenses also that heat transfer fluid essentially. Right? Maybe, I'm not so sure.
If I comment, sometimes it's also due to the cooling power, and sometimes you have also the need of an electric power to keep on this.
Right.
So, for instance, in Icarus, when we were in Gran Sasso, it was quite extensive power. So sometimes it's better to start with direct cryogenic fluid.
Right.
Nitrogen is not so expensive, and it's quite easy to have it also
Right.
underground.
Right, it's easy the supply is simple, so yeah.
Yes, so there is another question. I see, no, other 2. Matthew?
Hi, can you hear me?
Yes. Mm-hmm.
Thank you very much for the talk. My questions were kind of more organizational. So how many of your parts do you buy from just a supplier, and how many do you make yourself? And then in your experience with the xenon experiments, how long does it take to kind of set up a cryogenic system like this?
Right. So I would say most of the components that that I showed, for example, there are very few that you end up building the component itself. Is so I would say maybe the system, of course, because you design yourself and you decide exactly how you want, so that you cannot have a company that manufactures the whole system because there's no essentially commercial applications for it. But the components themselves, it's almost always possible to get. It's not off the shelf, but it is made to order components that are more expensive than the traditional ones, but it's always possible to find. Very often, the thing that the intersection where what I'm saying, like the little caveat of what I'm saying is the low background, and then so the need to be careful about impurities, and specifically radon being released in your detector. This you can be lucky. It can be that just, for example, gas purifiers with non-evaporable getters, they're not so they don't release that much radon, so you can use them, and it's not too much. But there's other components that is just pumps in general. It's not easy to find gas pumps that are very low. So that's why a custom one was built in our case. Then for the second part of your question, I would say that it depends a lot on if you know in advance exactly the requirements and all of this. It's I don't know, maybe something like a year or two, the design, the construction, and let's say if you know exactly everything from the beginning, maybe design construction can be a year and a half or something like that. But if your requirements are not super clear and you need to think about it more, and then it can easily stretch to 2 years, 3 years. So in the case of in our case, because we did not have a cryogenic liquid purification system before in the previous instance for 1 ton, then doing the R&D, understanding exactly all the requirements, knowing what is, as I said before, knowing how much impurities you're going to release tells you how much, which speed you should purify, which tells you how big your filter should be, and all of this. So until you have all of that clear in a model that allows you to some degree to test the designs, that can also take a bit of time. So it's then there's also the commissioning, and these things can mean that you have to understand some things before you can decide exactly how to build it. But yeah, I would say roughly speaking, sort of couple of years, I guess.
Okay, thank you. There is another question. I think we have time. Ibrahim?
Yeah, hi. Can you suggest how to minimize the cosmogenic production of 42 argon in the liquid argon? Because that creates a background of 42K in our latent germanium experiments.
Oh, how to reduce its production, or how to remove it from the fluid, you mean?
Reduce, I think that's most better.
Right. Okay, I'm not at all an expert on what is the production mechanism exactly for this one.
It is cosmogenic. It is cosmogenically induced. So okay. You have to go underground.
Right. Yes. Then the only way is to either find a source that has been shielded for a long time, or depending on the decay time, wait. For xenon, we do this, and usually, for the experiment, you procure the gas ahead of time and you leave it in an underground setting so that you don't activate. Sorry, it's a little bit out of my let's say strong expertise.
I think Cristiano Galbiati tomorrow can answer also this question.
Right.
So I think we have done. I don't know if there are some quick questions. Otherwise, we can also stop here. I don't know, Walter, if you agree. And I congratulate again with the speaker, because you were really good and you did a lot of work for this talk, and it was really interesting. So thank you again.
Thank you.
So please put the slides, and if you can participate to the discussion session. I don't know if there will be some other.
Yes. I'll be here for the. It's at 6:30, right? Yeah.
Okay, so I think we have a break, and we can come back in half an hour. Thank you very much, everybody.
Thank you.
Francesca, it's Marco Selvi. Are you around?
Marco, I'm Matteo. I'm here.
Hi, Matteo. So the next speaker, Oliviero Cremonesi, would like to check if the screen sharing works okay. And so
stop sharing.
Can we make? Okay. Thanks.
So we can also try.
Okay, so now I'll get in touch with Oliviero. Yeah, he's trying. Okay.
It seems to work, yeah.
Is it working?
Yes.
Yeah.
Can you see also
Try
the mouse?
the full screen. Yeah, perfect.
Okay, that's perfect.
Okay, great. So, yeah, I think we will start in 5 minutes. But
yes, I can leave it in case the sharing. If you prefer, yeah. I can take away the sharing, but since it works, I prefer to leave it there.
Okay.
Okay.
We can wait for a while.
Yeah, hi Chiara. So we just checked the screen sharing of Oliviero, but it's working. So then it's up to you to start the session as soon as it's time.
Yeah. Okay.
Thanks.
We can wait a few minutes more. Okay, thank you.
Yeah.
Let me try one thing. Stop sharing.
Okay.
Sei a Gran Sasso?
In questo momento sono a casa.
Ah.
Sempre al Gran Sasso.
Me too. Mosquitoes and hot.
Sì.
As you will remember, probably.
Yes. For this reason, I moved from Milan to Gran Sasso.
A good choice. But Pavia is worse than Milan.
Yes, even worse. For this reason, I moved from Pavia to Gran Sasso also.
Exactly.
Wait 2 minutes more just to arrive at 4:45.
C'è una roba.
The number is increasing quite fast, so maybe in 1 minute we can start. I guess that for some students, this hour is not really nice.
Yeah.
Okay. I don't know, Walter, do you think we can start? We have to wait for a while.
I think you can start.
Okay. So I'm a bit excited to introduce Oliviero, as I was a student of Oliviero during my degree. So it's a strange situation for me. And he was very hard as a teacher. No, okay, but Oliviero is a senior scientist of INFN. He's also teaching in Milano Bicocca University. He's an expert of underground physics. He was working in SASO since the very beginning, and he was one of the father, if you want, of very important detectors such as Cuore experiment, for which he was also spokesperson for quite a lot of time. He is also member of Cuore collaboration. Cupid collaboration, sorry, and now he has an important role in FN, that is the one to be the president of the scientific commission that decide which experiments to be approved and which amount of funds to be given to these experiments for INFN, the so-called second commission IFN. So he is an expert in the field, an expert of both underground physics, but all the astroparticle physics. So I am glad to introduce him for this lecture on statistics for underground physics. I asked Oliviero if he wants to be to have a break during the presentation, or if he wants to go straight to the end, and if he wants to be interrupted for questions, or he prefers to have the question at the end.
Okay, let's see for the break. In the sense, I believe break is useful, but let's see how I proceeded. For what concerns instead the questions, I believe you can interrupt me when you like.
Okay.
The problem is that I do not see any raised hand, so someone has to tell me that someone wants to talk.
Okay. Thank you very much. So you
okay. Thank you, Chiara, also for remembering the good times. I hope I was not too tough with you, but for sure, I'm a senior scientist now. That's correct. Okay, statistics for underground physics. It's true that I'm also a teacher at the University of Milan, but not about statistics. So this is my first lecture on statistics, and I hope it will be amusing for me and for you. I mean, it's a good experience for me just to transmit, let me say, a lot of experience gained in the years, even though I'm not considering myself an expert in the field. For sure, I'm using statistics since a long time. So this is the outline of the two lectures. I mean, the first one will be devoted to fundamentals in probability and statistics. So the relation of these disciplines with measurement and physics interest, and then probability, random variables, PDFs, and bias theorem, which are the most relevant ingredients to understand also the following. Today, then, we will look for the estimators, and in particular with the likelihood estimator, so parameter estimation and results combination. Tomorrow, instead, we will go to one of the most debated items in statistics, which is the p-values and the statistical tests. And if there is some time also to get a view of the procedures for getting limits. Finally, I would like to devote some time to a recent discipline, which is Markov chain Monte Carlo, just to give an introduction to this procedure, which is based on not Bayesian approach, but which is very powerful, and it is being used in underground physics for a lot of applications. So the first disclaimer, I already said I'm not an expert in statistics, so do not believe I will bore you with theorems or so what, let me say. And I will try to give you ideas and maybe some rules which are useful in the analysis of the data. Then maybe I'm more a practitioner, so rules will be given with a bit of experience and not of mathematics behind. So I hope this will make the lecture also more easy to understand. And finally, part of the material has been drawn from presentations and from documents from Roger Barlow and Giulio D'Agostini mainly, but also from a wonderful work of Oria, written for the first time in the 50s, but still very, very useful on likelihood ratio, and some information about statistics from Cowan and James. I suggest you also some books which has guided me not only for these lectures. So Barlow is, in my opinion, a very good book. Then Agostini is a guru of Bayesian reasoning in Italy. So if you like to understand more about this, I believe you have to read his book. And finally, 3 standard books on statistics, let me say. So let me start. Statistics, why we need it. To understand this, I believe we have to understand what is our interest, what we try to do every day in our activity as experimental physicists. So we start from theory. So we have a model behind every hour measurement. So gravitation in this case and elongation of a spring. Then we build our experiment, in one case, balance, and then we do the measurement. Okay, we measure our weight or what you like. If we go to more complicated things that we heard probably this morning, you can have very complicated theories which are predicting unexpected behaviors. So you are not starting from something known, but also from something that you don't know. So you have to verify the compatibility of the theory with the measurement. Then you build your experiments that can be very complicated and which need, for example, complicated simulation in order to understand how the behavior of the detectors arrives in producing data. And finally, you have your data. Okay, you have selected your data that usually result in spectra or histogram like those indicated here, from which you would like to go back to the origin. So you would like to understand if these data are able to give you information about the origin. So as you can see, is that 2 ways around. So you go in one direction and you decide to go back. And we will understand that this is very clear, but not very easy to obtain. With another example, the first one was from dark matter. But for example, in neutrino physics, which is one of the items I know better, one theory predicts that in case neutrinos are Majorana particles, you can observe a given behavior of your detector. You can observe a line at a given energy. So you build your experiment. This is a picture of Gerd at LNGS, and this is of Cuore. You can do, as usual, simulations in order to understand better how the detector works. So in order to be sure that the measurement will be correctly interpreted. And then you finally have your spectra from which you have to extract the information. So probably you are used to think that statistics enter here, okay, enter here in the interpretation of the data. I would like to convince you that that probably we can do more, or at least what has been done so far is not enough to give an answer to this kind of problems that were described here. So if we describe the path from theory to the measurement, we have one thing immediately. If you observed what I presented before, the data are sparse. So a although you expect one exact line here, you observe instead a peak, let me say a Gaussian. So you have a sparse information that can go from the energy where you expect to see it until infinity in one direction and the other. Yes, for sure, the points outside the main line are less probable, but they are not zero. So if you see a count here, you can't exclude it is a count belonging to the peak. And this is mainly the most difficult thing in measurement, and this is the main reason why we need statistics. So let me continue. So the conclusion is that all measurements are uncertain. There is a book written by the Standard of Measurement, which explains why we got such a conclusion. But you can believe to me, and maybe you have already discovered by yourself. When you do a measurement, the result is always uncertain. So given one known source, okay, your measurement will be distributed in a number of values which are not unique, okay? And statistics will help us in doing this kind of path. So if you know the source, then you can understand how the data will be distributed. This is for sure a very useful and important path, okay? But it's not the whole story. Let me complicate a bit the situation. What happens is if instead of having one source, we have more sources, of course, each of them adds uncertainty to the measurement and makes even more difficult to go back to the source. So let me say, complicates the situation. Okay, in this case, of course, you can use statistics again, as we will see, to predict, given a certain source, how the distribution of the data will be. And so you can expect what the result will be on the basis of the source you are selecting. But I remind to you that our problem is another. We have data, we have a unique set of data, and we want to make inference about the origin of them. This is the problem. So given one measurement, so we make one measurement, we have an experiment, how is it possible to go back to the origin of the measurement? Okay, it's easy to understand that this is not possible. Okay, this is not possible, and the only possibility is to express somehow our confidence that the measurement was caused by one or the other source. And this is what has been done so far. So we need an instrument that helps us in going back from the measurement to the source. So I told you that statistics is helping you in going from the source to the measurement. Now we need a tool, let me say, from the inverse path. And what's clear is that when you have uncertain data and uncertain sources, of course, the path is very difficult. And we have to understand how to go back. So just to summarize all this long discussion, we have sources which are not known and produce a single measurement which is distributed in a given range with a given probability. For each source, statistics can help us in describing the population of these measurements. Okay, so it helps in describing this path. We will also know the details of this, but we need to go back. And statistics, unfortunately, is not the correct path for this, at least the usual statistics we know. If we want to go beyond this, let me say we usually parameterize our theory in terms of a given set of parameters, which are continuous, and we hope to get from the observations an estimate of these numbers. Usually it is only one number for each experiment, but it could be even more than one. And the important thing is that we can hope also to learn from our experience and to apply this to future measurements. This is not so inconceivable. I mean, statistics tells you that if you repeat a measurement, you improve the uncertainty in the result. But I'm referring to a different approach when I tell that from a given measurement, I would like to increase my confidence about the state of these parameters. As I told to you from the beginning, any observation gives to you only a confidence of the parameters. You all know that when you go to the university, everyone tells you have to put a number and the error represents the distance from of your number from the possible true value, which, by the way, is already a path back from observation to theory, but as we will discover in a while, is not so polite, let me say. Okay, so I believe I already said this, and let me only comment this last statement. Uncertainty and probability. So if we look at the previous diagram, we know that given a source, we have a probability to have a given measurement. And we know actually what probability is in that case. We know exactly how the population of measurement will be distributed. Usually you read on papers the probability that the mass of the neutrino is less than 1.1 electron volt is 90%. Have you ever asked you what does it mean? In the introduction I gave, this means that you have a confidence about the true value of the mass of the neutrino, and you have stated this in a statement like this. So you say usually that the probability that the mass of the neutrino is in the interval 0, 1.1 electron volt is 90%. Of course, such a statement is, let me say, normal to a physicist, and instead physicists have invented for this the so-called indirect probability, which is a series of tools working with probability for going back from the measurement to the source. Okay, but this is not acceptable by statistics guru, because for a guru the true value is there or is not there. There is no probability for this. I mean, you can't say that the neutrino mass has a probability to stay in that interval, or it is there or it is not. I hope this is very clear. So this is a very obstacle for the mathematics, let me say, for the statistics as a mathematical discipline, while physicists which are more interested to go back to this statement, of course, can accept this, and have tried to interpret the outcome of the measurements in a way that can allow you to go back to the origin of the source. This procedure is called inference, as I told you before, and tells you that given the past observation I'm reading, in general, we are not sure about the theory parameter, and this is uncertainty. Okay, but we want to have a confidence on what the outcome of the result can tell you about the true value, and especially of a theory, so the unknown. Our job is observe events and extract properties of particles. This is the first step. Then we compare observed distributions, which are predicted also by theory, with the prediction of theory, and estimate the free parameters of the theory. This is where we have the difficulties, and I will try to introduce how they can be at least faced. So we need to quantify the uncertainty in our estimates. And to do this, we have assessed the level of agreement between the observed data and the theory. For what concerns especially the underground physics, there are some issues which add to what I have already said. In particular, underground experiments are mostly interested in rare events, which means events that, of course, are rarely occurring. And because if they were occurring more often, probably they would be already discovered by other experiments. So we have to do with the small numbers. We have disturbed by noise in the ground, and of course, also by the uncertainties of the measurements, which I introduced before. In order to face this, we need probability and especially a coherent scheme. I go back to this. So probability is something that we learn continuously at the university, but maybe we have also to understand how to use these tools. And for this, we need to appreciate the different schemes in which they can be interpreted. So let me go to the definition. Statistics is a branch of applied mathematics. So this is the strong power of statistics. It's a discipline, a scientific discipline, and it helps you to, to estimate the population parameters given a starting hypothesis, given a starting model. The inferential aspects of statistics, as I mentioned before, are enhanced in the sense that you have a one-way inference. You know the source and you want to understand the population parameters. But in the other hand, in the other direction, let me say they are very poor. And the other direction, as I try to convince you, is the one where we are mostly interested in. So inference is the learning about theoretical objects from experimental observations, and this is our true interest. While probability theory is essentially okay for the mathematical apparatus, and actually we have all to know the mathematical apparatus because this path is absolutely important, and today I will introduce you to some of the most important results in this path from top to down. But then we have to, let me say, to go beyond the difficulties in the inference, which are at this level messy, because I don't know if I can invent in this moment an example, but suppose you have 3 different Gaussians. Okay, each one, I have not yet introduced the Gaussian, but I hope you know what is a Gaussian. So you distribute numbers from a given, you generate, numbers from a given Gaussian, and you observe one of them. It should be very clear that it is impossible to understand to which of the 3 Gaussians the number belongs, or at least from which of the 3 Gaussians the number was extracted, which is one of the difficulties I mentioned before. But this is our goal. We have 3 hypotheses. All 3 hypotheses are possible, okay? And we want to go back and from one measurement to say, what is the Gaussian from which we extracted this number? Okay, let's start the path to this. Are there questions on this part?
No, I think we can go on.
Okay, probability should be an already known item, so I will hope to go more straight in this. The basics of probability is that probability is an axiomatic theory. It is based on 3 axioms from Kolmogorov from the first part of the previous century, and essentially create a function P which has these properties. So it's always positive for any subset in a given space. The probability is less or equal to 0, and less than 1, which is the total probability of the space. Then we have a fundamental property, which is for the intersection. So if we have 2 sets and we want to calculate the intersection of the union of these 2 sets, assuming that their intersection is the empty space, then this is the sum of the two probabilities. So the sum of the union is equal to the sum of the probabilities when the two sets are not intersecting. Then we can define a very important item, which is the conditional probability. What is the conditional probability? The probability of an occurrence A once the occurrence of B has been done. So in case you have already an event which belongs to B, you want to understand what is the probability of A. And it can be demonstrated, it's not so difficult, that this is the intersection of the two events, of the two populations, let me say, divided by the probability of B. Apparently, this expression doesn't tell you much, but this is a very important result. Okay, in particular, if we go back to the case where two events are independent, in this case, you can demonstrate that two events are independent when the probability of their intersection is just the product of them, okay, of the probability of each of them. This is a definition, let me say. So you say that the two populations are independent when the probability for their intersection is exactly the product of the probability of A and the probability of B. This should be quite natural, but if not, try to reason on it. If you accept this, you can discover that the conditional probability of A given B is given by the product of the two, and it is equal to A, which is quite, quite obvious. I mean, if an event is completely independent of A, the probability of A given B is independent of B, and this is exactly the probability of A. Okay, so let me come to the two main schemes above which statistics has been built. The first one is the oldest one, is the mathematical discipline I mentioned before, and tells you that the probability is a relative frequency. So you define a way to obtain the probability by thinking to an experiment in which you count the outcomes of a repeatable experiment, and you have the ratio of the outcomes of a given event on the total. Most of the criticism in this definition is in this repeatable experiment. It can be rephrased in many ways. They are all possible. They are equiprobable, in sometimes it's also said. So if you repeat n experiments which have all the same probability, then the probability of A is the ratio of the two, of the positive case of A with respect to the total, which of course is a bit problematic as a definition, since it contains probability in the definition itself. This is most of the criticism to the relative frequency interpretation. Then we have another interpretation, which is subjective probability. What does it mean, subjective probability? It means that if you have to bet on a given outcome, you would use this kind of probability. So the probability of an event A is your degree of belief that A is true. This is based on, or can be based on many things, on the relative frequency, on a priori situations, on previous measurements, and so on. Let me give you an example. If you want to bet on a coin flipping and going head or the other side, you know that you can bet 50%, so your degree of belief is that in 50% of the cases you expect the coin to fall with a given face. So this is not so bad, but this is not particularly appreciated by physicists because, of course, being subjective, the definition of PA can be decided by the experimenter. So it's not, let me say, an absolute thing, but I let you understand that also the relative frequency is not an absolute thing. In many cases, when we speak about statistics, we are looking for asymptotic properties, and we are working very far from them. So we are working in a condition where, in any case, we have approximations. So to be honest, I do not understand this kind of war of the two interpretations. For sure, the most used so far is the relative frequency, but as I will try to demonstrate to you tomorrow, there are aspects in the subjective approach which are much powerful with respect to the relative frequency. So let me say, it's stupid not to consider them. Let me conclude this long discussion. Both interpretations are consistent with Kolmogorov axioms, so both of them are correct as in terms of probability, and both of them are pro of cons. The pro of the relative frequency is a very powerful mathematical environment. It is largely diffused, but the subjective probability, which is what is known usually as Bayesian approach, has many cons with many pros, sorry, with respect to our way of interpreting measurements, and I will try to demonstrate this tomorrow. Let me start today with the frequentist statistics. So I told you that in the frequentist statistics, probability are associated with the data and the outcomes. The frequency of the outcomes is defining the probability of them. So as I told you before, we can say that the probability of having a given number of head in 10 launches of the coin is given, but we can't say anything about statements like those I put it before. Then let me point out a very important thing. A hypothesis is preferred if the data are found in a region of high predicted probability. What does it mean? It means that since I can predict the population of a given experiment, for example, I can predict that that if I launch the coin 10 times, most probably in 5 cases I will get head, and in the other face. But I can't exclude that I have also regions which are less probable. For example, having 10 faces in 10 launches. I mean, the probability is very small, but it is not impossible. So according to the frequentist statistics, this is an occurrence which is less probable, and we are using this, for example, to test hypotheses and to discard this hypothesis. So let me make you another example. You are playing with your best friend, okay, and after 8 launches of the coin, he gets 8 heads. What are you thinking about that? What is your feeling about this? If you look at the frequentist statistics, you are telling to your friend that he's kidding and you are losing a friend. If you are looking to a different approach, maybe you can have some more things to evaluate this part. So I believe that many of the problems we had also in publications are given to this approach, and I believe we have to do something in order to go beyond this and to have something that it is not simply creating p-values, as we'll discover tomorrow, but it is actually saying us what is the confidence that a result or a theory is wrong or right. Okay, finally I arrived to the Bayes theorem. The Bayes theorem comes directly from some of the properties I said before, and particularly if you mix these two, or if you prefer, if you understand that this property is symmetric, then you can invert A and B and obtain these two. Then if you equate the two numerators, you obtain simply that PA given B times PB is equal to PB given A times PA. Okay, or written in a different way, PA given B is given by PB given A times the probability of PA divided by the probability of PB. What's the meaning of this theorem? Apparently nothing, but instead is very important, and we will discover in a while. This was published for the first time very long time ago, more than 200 years ago, but it is still at the basis of our interpretation, of our possible interpretation of statistics. So let me rewrite the theorem in a different way. To do this, I divide the total space in subsets, which are I don't find the word for this. In any case, okay, the intersection is nothing, is null, and the union is the total space. Okay, a partition. Okay, a partition of the total space. Then I can write B, which is our red curve here, as the intersection of B with S. Then I write S again as the union of all the partition subset, and using the property of union and intersection, I can arrive at this conclusion. So B is the union of the intersections of B with the A. Okay, so I can write PB again as using the laws I wrote before as the sum of the probabilities of the intersection of B with each one of the partition ensembles, which means that I can write PB as the sum of conditional probabilities. If you remember, PB was the denominator of the Bayes theorem, so I can rewrite the Bayes theorem in this way. Why is this important? Because in this way, this is somehow a normalization term. I mean, it's the total probability of B, and we can write simply that PA given B is proportional to PB given A times PA. Let me come to our interest in this. I rewrote the Bayes theorem by using different terms. So the probability of a given cause, of having a given cause given the data is the probability of the data given that cause times the probability of the cause divided by the probability of the data. This term is the one in which statistics helps us very much. I mean, it's very easy to evaluate. If we know the cause, as I said before, statistics gives you a very powerful tool to evaluate this probability. So what is the probability of a given occurrence? But what is most important is that we are interested in this one. As you remember, I was saying that given our data, given our measurement, I would like to understand what is the cause of this data. So we can invert the reasoning. And to do this, unfortunately, we need to have two additional terms, which are the so-called priors. In particular, the most critical prior, which is a prior knowledge of the cause, is the subjective part of this approach. So inversion is straightforward, but we need priors. And let me say, once the priors are needed, there is one more things that should be clear. If I use iteratively this theorem, I can change the prior. I mean, this can be easily demonstrated. I will not do this today, but this is another way of saying that the probability is subjective and can change. It's not an absolute property of the cause and can change in the future. So if you start with the temperature in this room, you probably can say, okay, probably the temperature in this room oscillates between -30 and +50 uniformly. Then you observe along the years the behavior of the distribution of the temperature. You look in this period what is, and you have a confidence which is changed, and you can use this confidence here. I will have a very illuminating example in this later. So statistics is working here. Bias theory can help in going in the other direction, but let's avoid philosophical discussions here. So the Bayesian statistic general approach, what is? We have data, we have hypotheses, and we want to infer one hypothesis probability given our measurement, knowing what is the distribution of the data given that hypothesis, and the knowledge of the prior probability. So our confidence about this hypothesis. As I will try to show, this is not so strange. The denominator is just the total probabilities, and as I said before, can be even forgotten. I mean, as we will discover, what is important, and it is also a classical tool for normal statistics, is the ratio of this probability. So you would like to understand what is the ratio of the probability of hypothesis H with respect to hypothesis M, let me say. And in this ratio, of course, the normalization factor cancel, and you can avoid it. So this is the most important expression of the bias theorem. Here is the example. I wanted just to avoid referring always to the COVID-19, because usually this example is done with the COVID-19. So let me put it in a different way. Let's consider the anti-terrorism tests, which are carried out regularly in the airports. And let's suppose the terrorists are carrying explosives. In this case, they are positive to the test of the powder, okay? We know that the test is very effective, but not perfect. So we know that if you are a terrorist, the probability that the test gives a positive answer when you are a terrorist is practically 1. So it's not failing. But when you are not a terrorist, there is 2% of cases in which the test fails. So it gives you a false positive. This is usual in tests. So even if you are not a terrorist, you are resulting positive. While in 98% of the cases, you are safe, let me say, you are negative. Now, I suppose you tried already at the airport to wait for the answer. And my question is, how did you feel in those conditions? In case, I believe you were happy when you discovered that you were negative, but what do you believe it could happen if you could be positive? Or if you prefer, what is the probability that in case you result positive, you are considered a terrorist? I made considered because you are a terrorist is very different. I mean, in these conditions, if we look for the usual statistics approach, of course, the police takes you and puts to the jail, because the probability that you are positive and not a terrorist is very small. But if we use the bias theorem, we observe another important item in this expression, that if the, I mean, this is true, but if the alternative, let me say, the alternative condition, the alternative option is not so probable, there is something which are mistaken here. And instead, and in fact, let me put in this way. Let me put a guess for the probability of terrorists and the probability of non-terrorists. Of course, you know that not all people on the earth are terrorists. I guess you can do is 1%, 1 per thousand. In any case, it's a small fraction. Even the number of people going through the airport with bombs are a small fraction. So you can have a good guess that the probability of finding a terrorist is very small. Okay, then if you build a so-called likely ratio, the probability of being positive if you are a terrorist, divided by the probability that you are positive and you are not a terrorist, you discover that the probability strongly depends, of course, on the guess you did for the probability of the terrorist, but it's not as small as you expected. Is something more. I remind you that this is a ratio. I mean, this should teach to the police in the airport to be more kind with people when the outcome is positive, and on the other hand, that if you are not a terrorist, you should be confident that you will not be you should not be arrested. Let me say. Okay, so the lesson from this example is that if the alternative is a hypothesis, so if the probability of terrorist is very small, then data found in a region of high predicted probability can be irrelevant. Okay, so the test positive for this is for a non-terrorist, not for a terrorist, is irrelevant. I believe we can stop here for a while.
Yes.
And we go back with a more, let me say, mathematical part, which is distribution. Let me say 10 minutes.
Okay, so we can reconvene in 10 minutes since now, if this is okay. So it about 10 minutes is about 40 past 5. Okay, thank you.
Okay, thank you to you.
Okay, so if you are ready, we can start again, Oliviero.
I'm ready. Thank you.
Okay.
Let's restart. So the philosophical introduction has finished. We can conclude that we have two approaches. They are equivalent on the one direction, which is from sources to data, but they are very different instead in the other direction. So you have to expect differences mainly in the inference part. Okay, the rest of the lecture today is on mathematics. So it will be, let me say, more straightforward, but also maybe more boring. Most of the things probably you already know, but they are needed and I have to be sure that you know them. So let me start with distributions. Since we have random variables and probability distribution of population, we need to know what is the so-called density function for describing these populations. This is usually expressed as the probability of an outcome being in a given interval. And this is expressed through a function, which is called the PDF. So when we call PDF, we mean the function which describes the probability of an outcome of a given experiment, let me say. And it has to follow the laws of probability. So the total probability has to be 1. So the integral over the whole space is equal to 1. And of course, the dimension of f dx are x to the minus 1. Of course, we have also discrete experiments, so experiments which gives you only discrete values. Let me say counting is a very important example for them. In these cases, you have discrete values for this probability, but the properties are the same. So you have to conserve the total probability, so the sum of all the possible occurrences of the probability has to be 1. With this introduction, we can define, when we go to more measurements, so to not just to a variable, but more variable, a joint probability. What is a joint probability? It's the probability of having n exact values of the random variable. So x1 equally exactly to a given number, x2 to the other, and xn to the other. It's a very complex function which describes the interaction between all the variables. Sometimes we start from a joint PDF, but we are only interested to a fraction of the variables. A classical case are so-called in the frequentistic approach, the nuisance variables. So you integrate over non-interesting variables, and you get the distribution, the marginal distribution, only on the variable of interest. This distribution is called marginal PDF, and the operation is marginalization, which is very common in Bayesian approach. Then finally, you have the so-called conditional PDF that now should be not a mystery to you. So the probability of having an outcome of the variable x1 given the outcome x2 of the other variables. And this is given by the joint probability divided by the probability of fx2, which is one of the consequences of the probability we have introduced before. Then another important point is expectation values. What are expectation values? Since we are working with different outcomes of a random variable, you have to average on them. And usually this average is indicated with E to mean ensemble. This is a mean ensemble mean, which means that you gather information from a population and you average the values from the population. But this is equivalent in terms of the PDF to this operation. So to the average of the given variable on the PDF. This is this is an average, this is an ensemble average. And in a so-called ergodic system, they are equal. So we will consider always one or the other to mean the same thing. So, or meaning that we are doing an ensemble average or an average through a PDF, for us it will be the same. The meaning, for example, of the ensemble average of X is the average, the center of gravity of the distribution. And you have to note an important property of this. If you have a function of X, so you start from a random variable and you build a function of X, then you have the average, the ensemble average, or the average of the variable epsilon, which of course is also a random variable, is given by this expression with the probability distribution with the PDF of X, which is a very important and we will probably use later. Then another very, very important average is the variance. These are the two most used variance in statistics, which is essentially, the definition is this one, is the ensemble average of the X minus the average value, okay, to the square. But it can be easily demonstrated that this is the ensemble average of X squared minus the square of the mean. And from the point of view of measurements, this is very important because it gives you the standard deviation to the square. Okay, so the meaning is that in a world which is mainly Gaussian, these two variables gives you the position of the Gaussian and the width. This is why they are very important. Then we go instead in a more complex, from the mathematical point of view, situation. I will try to build some example later, which is the covariance of two variables. What does it mean? It means that we are working often with variables which are not independent. The outcome of one depends on the outcome of the others, which is called correlation. Then also the errors on a given measurement depend on the value and on the errors of the other. And this is expressed through a matrix. This is a matrix which is called covariance, or matrix of the errors. And this is defined as the averaging, the ensemble average, as indicated here, of one variable minus its average and the other variables minus its average. This is not very easy to visualize, I understand, and this is why usually one doesn't like to work with covariance. But let me say it's important to know that it exists and to be aware that we have to check always about correlation of parameters, because the results can be very different. A very useful definition of covariance, which is related to the definition of the average, is this one, in which you have that the covariance is defined as the ensemble average of X times Y minus the product of the two averages. We will discover later that there is a very direct way to obtain the covariance matrix of X and Y, and this is one of the things I would like to address to you as an important point today. Then there is the so-called correlation coefficient instead. Let me say, covariance means errors. So it tells to you how the errors on one variables influence the other and vice versa. The correlation coefficient instead tells you how the data are correlated. So how changing one, you obtain a given change in the other. Okay, and the important relation is that there is a very straightforward relation between the covariance and the errors, the standard deviation. In particular, the matrix of the correlation matrix is given by the ratio of the covariance to the errors on the two channels, let me say. Okay, then of course, if the two variables, two random variables are independent, then the PDF is the product of the two PDFs, and you can easily demonstrate that the covariance is zero, if you prefer that the correlation is zero. This is somehow a definition of uncorrelation, and of course the correlation coefficient has to be zero. These are examples of clarifying what's the meaning of correlation with two variables x and y. So this is a positive correlation, quite strong, very close to 1. This is a negative one. When you increase one, you decrease the other. And this is a very strong correlation, positive, between x and y. And this is instead a very weak. So the lesson from this is that when the correlation matrix is small, the data have a very weak correlation with one between the others. Of course, I try to summarize most of the properties that are useful, but I don't want to discuss with them. Let me just try to put the accent on them. We didn't mention the mode, which is very important. The mode is the maximum of the distribution. So the max value of the PDF is called the mode of the PDF, while the median is defined as the value of x for which the probability before that value and after that value is equal, and is equal to 0.5. So these are the three most used let me say parameters. And let me say the most used is the mean, essentially because most of the statistic theorems are concerning mean. All the measurements instead are concerning mode. So please pay attention to this statement. When you quote a measurement, you usually quote the mode and the standard deviation, while the theorems which combine results usually combine means, not modes. So you have to be very careful in this respect. Remember this comment. Then the scale and other properties, I believe I can skip. Let me only remind to you that moments of a distribution are quite important when you want to understand if you are looking for a distribution or not. For example, the Gaussian distribution, which we'll encounter in a while, has very simple properties. The logarithm of the Gauss has just the zero term and the second term. So all the moments of larger order are zero. So if you are looking for a distribution which is looking to a Gaussian, you can discover it immediately by going to larger moments. So a skewness or a kurtosis which are different from zero mean that you are not working with a Gaussian. You already mentioned the covariance, so let me go ahead. Central limit theorem. This is a wonderful and very important theorem of statistics with very, very, very many consequences. What's the statement of the central limit theorem, which is mentioned in many occasions? I read it. Suppose a random variable x is the sum of several independent and identically distributed variables. This is important, identically or similarly distributed variables. So you have variables x1, x2, x3, xn, which are extracted from different PDFs, which have only one request. They have to be very similar, okay? Then what do you obtain? The mean of this distribution, the mean of the sum, is the sum of the means, okay? This means that if you sum, for example, a number of square distributions, you, in the end, with the large number, you get a Gaussian which has a mean, which is the sum of the means. And most importantly, the variance is the sum of the variances, okay? And the distribution is Gaussian. I mean, this theorem is always used if you want to do an exercise, maybe even in the hand-on session. If you take the uniform distribution for the Monte Carlo generation, and which uniform deviates, gives you a number which is uniformly distributed between 1 and 0, and you sum 12 of these numbers, what do you get? Too difficult? Okay, the average, of course, is 0.5. So the mean is 6, because 12 values, average 0.5 means 6 as an average value. But then what about the variance? The variance of a square distribution is 1/12. That's why I decided to sum 12 values, because with the sum of 12 values, you obtain a variance which is 1. So by summing 12 numbers which are distributed uniformly between 0 and 1, you get a Gaussian distribution which has sigma, standard deviation 1, and average 6. So if you subtract 6, you get a normal distribution. Wonderful. What is the defect of this? Of course, n is not so large, 12. So where do you expect deviations from the Gaussian? I can assure you that they are not in the shape of the Gaussian. The shape of the Gaussian is, let me say, quite good. But the problem is that if you sum 6 numbers from 0 to 1, the maximum number is 12. 12 numbers, the maximum number is 12, which means that the tails of your Gaussian are stopping after 6 standard deviations. This is the limitation. So if you want to improve, you have to add more numbers. Okay, I have no time to discuss more in details. I put here proof of the central limit theorem because it's quite simple, but I have no time to discuss it. But if you are interested to look at it, it's very direct and simple, and it is extraordinary that such an important theorem has a very simple demonstration. Let me come now to some distribution, with some example also of application in high energy physics. As I tried to say in the introduction, the title of my lecture is Statistics in underground physics, meaning that usually you intend with these small numbers, but I can assure you that small numbers are also a general property of high energy physics, also for accelerators. So this is a general statement. Okay, the binomial distribution, which we discovered in a while, is describing coins, the launch of coins, is also describing the occurrence of decays, branching ratios. Then the multinomial is very important because it's describing spectra, histograms. The Poisson is maybe the most used distribution, and it is the counting experiments resulting in histograms, as the one I showed you before. The uniform deviate is the basis of the Monte Carlo method. The exponential is the basis of the decay, of the law of the decay. The Gaussian is the measurement error, and it's pervading our life. Let me say, everywhere we found Gaussian, and even when we don't find Gaussian, everyone is telling to you that with large numbers we reach a Gaussian. And then we have less important, less used, let me say, not less important, Cauchy or Lorentz, which is of course the so-called Breit-Wigner, the Landau, beta, gamma students. Okay, let me skip on them. So Poisson. I hope everyone knows this distribution. This distribution tells you what is the occurrence of error counts when on the average you expect mu, okay? And this is given by this simple law as to the minus average times mu, okay, as it is written. It's easy to read and tell it. As I said before, it describes a lot of experiments, all the counting experiments, but also most of the behavior of the detectors, in particular shot noise and so on. Not, for example, photons from lasers, because they are not, they are, I don't find the word, sorry. They are correlated and they are not, they're following this distribution and the traffic also. They are quite good counterexamples. values. The vital factor of the Poisson is the standard deviation, which is equal to the square root of the average, and that's all. Let me say, because there is not a rule for the mode, because this depends strongly on the value of mu. So if mu is less than 1, the mode is 0, and it increases when mu increases. An important thing is that this is a discrete distribution, because usually R are integer numbers, but there is an extrapolation of this function with the gamma functions, which gives you also the factorial for real number and allows you a generalization also of the Poisson. In any case, for what concerns statistics, this is the only distribution that it's important for us. Important things to remember is that if you convolve a Poisson with a Poisson, you get a Poisson. So if you add two Poisson numbers, you obtain a Poisson number. If you convolve a Poisson with a binomial, you get still a Poisson, okay? And there is also another property which I didn't mention, but I was convinced to have written, but it is not written. Maybe when I arrive to the binomial. Okay, nothing to say about the Gaussian, apart from the expression, which should be known to everyone, and the meaning of the areas under given intervals of the Gaussian, which are very important because this is the most used distribution in statistics. It's very important to know and to remember what are the values of these areas, as we will discover in a while. So,
Almiro, sorry,
yeah?
There is a question. I don't know if you want to answer now. I asked Philippe to express your question.
Go ahead.
Thank you very much. This is very interesting. Just you referred to a continuous distribution of the continuous generalization of the Poisson distribution by replacing the factorial with a gamma function. Is it trivial to normalize that? Is that well known, or?
I'm not sure I got your question. I mean, the generalization with the gamma function let you define the Poisson distribution also for real numbers. But that's right. But in our case, which is useful for some demonstration, for example, because you can use analysis, calculus, but for statistics is, let me say, almost irrelevant for the applications in our cases.
I understand that. But my understanding is, to be sure that it's a distribution, for instance, you have to check that it's normalization. In other words, the integral is equal to 1. And is it trivial to show that with the inverse of a gamma function?
I don't know. I have not an answer. I can check this.
If you have any references, I'd be happy to see them. Thank you very much.
Thanks to you.
We can go on.
Okay, thank you. Okay, the examples from the use of Gaussian are infinite, so I skip them, let me say. The binomial is very important, maybe not so used, but it's very important. As I mentioned before, it can be used for branch ratios, but not only. Usually it's used for coins or for the generalization of the Bernoulli process. But so it's very important in statistics, but I believe it's very important also on physics. So please remember these two properties. The average value is given by the product of the probability of one event times the number of trials, and the dispersion and the standard deviation is given by the square root of the products of the two probabilities times the number of trials. Okay, I already said. This is what I said before. The uniform deviate is a distribution which is uniform between 0 and 1. And the important thing is that it is given by the width of the interval divided by the ratio by 12, the square root of 12. So again, if you add, so the variance is 112. If you add 12 numbers from this distribution, you get a Gaussian, which is normal, so with the standard deviation 1. This is a very important distribution, not very used, not very known, but this is very important. How it can be used? I mean, imagine this P1, P2, Pm are the elements of your histogram. okay? So the probability of each histogram is your model, what you expect for the bin 1, bin 2, bin n, okay? Then you do the measurement and you look to the outcome, and the outcome is a series of numbers, n1, n2, n3, which are the contents of the different bins. The distribution of these bins is given by this law, which is an extrapolation of the binomial, in which you have different probabilities, just the models for the content of the spectrum, and a coefficient, which is the classical combinatorial coefficient. This is very important, and as I said, it's not so used, and it should be more known, because when you have very low statistics, this is the best distribution to be used, much more than the Poisson. So let me say, when you are looking for small numbers, the first point is multinomial, then you can try Poisson, and then finally, if you have large numbers, you know that Gaussian is always working. Also here, let me remind most of the most relevant properties, which as usual are the the average, the average or the ensemble average, and the variance, which is related to the probability of each one. And the demonstration is very easy if you know the result from the binomial, simply considering one bin with respect to all the others. Of course, in this case, you can have correlations between the different bins, so it's important also to define an error covariance matrix, which is given by this. These properties are not so easy to demonstrate, but I invite you to take a look to them and to try to obtain them. Another very important exponential distribution. Why it's important? Not only because it's describing, let me say, the law of radioactive decay, but because it has a unique relation with the Poisson distribution. I mean, Poisson distribution means usually that every point is equivalent. Okay, so you say usually that a Poisson, a population is distributed normally, with a Poisson distribution if each value of x is equiprobable. Then, if you look at the distance between the different outcomes of a Poisson distribution, you discover that the distance is distributed with an exponential. So there is a very clear relation between the exponential distribution and the Poisson. So please remember this. When you want to distribute, for example, numbers in a Poisson way, you can decide or to generate randomly the values, or distributing with a so-called interval distribution or exponential distribution, the distance between one and the following. Useless to say, very easy to obtain the average value and the variance, so I skip this. And the multivariate Gaussian, of course, is a Gaussian in more dimension. The only reason I put this is that it can be expressed through the variance, through the covariance matrix, because in this case you can have correlations and dispersions around the axis, and there is a matrix notation for this, which is very useful. So in this case, it's much more useful to define the average on each axis and the covariance, which is related to the dispersion, so how the numbers are dispersed with respect to the average. Okay, let me come then to the chi-square. Needless to say, it's an important but not so used distribution, because it's very important because like the Gaussian, many theorems provide an asymptotic behavior of some distribution in terms of the chi-square. So it's important to evaluate the areas or the probabilities to know this distribution, but otherwise it's not so used. The beta distribution is related to Bernoulli process. I never used it in my life, but just I put here for, and the gamma also for, okay, the t-student, it's probably used more in different areas, not in physics, and it's related to the, I don't remember the name, but chi-square distribution when you don't know when we are using the sample variance instead of a known variance. In that case, the chi-square is not distributed with the chi-square, but it is distributed with the t-student distribution. So you can forget about it. Estimators. It's time to go to estimators because it's late. So general properties. What do you imagine is an estimator? The estimator somehow is answering to the first question I raised in the first part of the lecture. You have a set of measurements, okay, or one measurement, and you want to have a guess of what is the source of this measurement. So usually you parameterize your model and you want to get an estimate of this parameter. So your population is characterized by a parameter, which is described by a theory, by a model. And from this outcome of samples, you want to have an inference, but an estimate. So you don't want, I mean, we have already discovered that it's impossible to have the true value, but you can have an estimate of the, of the parameter. And then later you will ask also how this parameter is close to the true value, so to the characteristic of the source. And this will be a following question. Okay, so let's go ahead. So we have a set of parameters, and the goal of the estimator is to provide a value of them which is close to, or which is the best estimate of the true parameter. Of course, we should be able to define in a better way this property. Okay, so the estimator is the method of estimation. The value we get from the estimator is called an estimate, and when you have a population and you express this with a number, this is called a point estimation. So very, very simple. Okay, the problem is that the problem is to find estimators. I'm not able to express why it's a problem. It's a problem because what you have to demonstrate is not for the moment that the estimates are close or not to the true value, but that the estimator has some specific property, and you want to define the properties of the estimators in a clear way so that later you can check if your estimator is the best choice you can have. Okay, so let me come. Let me come to the list of properties. Usually you require that an estimator is consistent. What does it mean it's consistent? It means that in the end it converges to a value. So you start with a given value, you get a population, the population gives you an average probably and the spread. And you want that the average value or the estimate is converging to a given value. Of course, you do not know yet if it is the true value. You simply ask that it is consistent. The second question instead is the unbiasedness. What does it mean that you want that it exactly converges to the true value? And this is, of course, a difficult question. We will demonstrate that some estimator are unbiased. That is, when we know the solution, we can demonstrate it converges to this solution. But in the real case, this will not be, in real situation, this will not be the case. And we will always have to check differently if the estimator has a bias or not. We will discover that some of the bias come from systematic errors, and the discussion will be tomorrow. Then minimum variance. So we would like to have an estimator which gives you numbers which are not so dispersed. And for this, of course, we will use properties, mathematical properties of the estimator in order to give an estimate of this. Let me say that it is impossible to have a zero variance, and it is impossible to have all the three at the optimum. So usually you can check, or you can get something which is a compromise between the three properties. So for example, we will discover that the likelihood is unbiased, but it's difficult to demonstrate it. I mean, I don't know if it is consistent, and there is a bound to the variance below which it's impossible to go, and we will discover what is it. Okay, so if we want to summarize, we can describe our population of parameters, X, which are the outcome of our measurement, in terms of a set of parameters, continuous parameters, theta. And the point is that we want to have an estimate of the values of theta depending on the value of the random variables. So our goal is to get the best estimate, we indicated with a hat, given a set of measurements. So we indicate the estimate of the function of X, and as usual, they estimate the actual value of the theta hat. And this expresses the value I said before. So the best is the one which has a small variance. It is unbiased because the true value is here, and the best has no bias. And it is also converging to given value. So we have to look to something which is similar to this. Okay, likelihood function and estimator. What are they? We can define what is the likelihood function, and then we should demonstrate that it is actually a good estimator. So in order to build the likelihood function, we need, as usual, to start from our PDF. The PDF is expressed in terms of a given set of parameters, which means if we know, given a set of parameters, then we have a certain distribution of the outcomes of the measurement, and the total probability is 1. Then suppose we have n such measurements, x1, x2, xn, xk, and we can build the product of the PDF of each value. This product is called the likelihood of this population. What does it mean? Actually, it's not easy to translate in a... Okay, let me... I mean, it's easier to demonstrate when you don't have a parameter, but you have an hypothesis. So if you have an hypothesis H and hypothesis H1, and you make the ratio of the two likelihood, this ratio is higher as long as the confidence of the numerator is larger than the denominator. So in some sense, the likelihood ratio is given to you an answer to our original question. So the confidence of a given hypothesis with respect to the other. We will discover in a while the relation between this and maybe and the bias theory. So how we build an estimator from the likelihood function? Simply by going to the maximum of the likelihood function. So if the likelihood function is expressing the likelihood of a given hypothesis, then it's quite natural to think that the best estimator is given by the maximum value of the likelihood. So we will indicate it with hat theta, the value of the parameter at the maximum of the likelihood. Okay? Of course, this is not the only thing in which we are interested, because as we have discovered before, we are also interested to understand how it is spread around this value. Okay, so we have a clear indication on how to use it, and we have to learn in a while the properties, or to summarize the properties, but then we have also to be able to evaluate the spread. And the spread can be usually evaluated by averaging over the likelihood function. So using the likelihood function as a let me say, as a distribution function, even though it is not a PDF. I mean, not in the conventional interpretation of statistics. Okay, but we can use this in order to get an evaluation of the spread of our estimator around the maximum, which is our estimate. Oh, well, now we can exploit one important property, which is logarithm is continuously increasing. So the maximum of the likelihood function is the same as the maximum of its logarithm. And this helps us very much. Why? Because it transforms a product in a sum, because the logarithm of a product is a sum. And so we have transformed a very annoying product which defines the likelihood. By the way, there is another property, but we will discover later, which is the fact that it tends to a chi-square or Gaussian. So it's quadratic, and with the logarithm, you transform in a quadratic function, a polynomial of order 2. Okay, so given these properties, we can find our estimator in a very straightforward and naive way. We derive the logarithm of the likelihood function, and we solve the system of equations. This is not always simple from the point of view of analytical calculation, but for sure it can be done very easily with numerically. So most of these problems have a very easy solution. And the easy solution is to transform a maximum of the likelihood in a maximum of the logarithm. But since most of the programs of the code finds minimum, you usually use minus W, and you find the minimum of W. And that's all. I mean, apart from now discovering the properties of this estimator, that's all we have to say. We have a possible estimator, which is the maximum of our likelihood. This is in 2 dimensions with 2 parameters, θ1 and θ2. And θ hat is simply the maximum of L, which is giving you a pair of parameters θ1 and θ2. As I said before, this can be done analytically in some cases, mainly academic examples, but in most cases, this is a very important item because most of the problems in physics are obtained through an estimate done with the maximum likelihood. So the likelihood is probably the most used estimator also because, as we will discover, it is unbiased and with a variance which is easily calculable. Oh, sorry, I shown the distribution. In this part, I wanted to prepare some examples. So let's consider the distribution of some event which expresses the outcome of decay, for example, for a radioactive decay characterized by the lifetime tau. Then the likelihood function is simply the product of these functions, okay? So you can simply build the product of these functions. This is the so-called unbinned likelihood function. And one of the requests for the unbinned likelihood function is that the PDF is normalized to 1, but there are extensions of the likelihood in which this can be forgotten for a while and recovered at the end. But this is detail, so forget about it. So if you start with a normalized PDF, you can build your likelihood. At this point, you have simply to go to the logarithm, as we did before, and this is very straightforward and very easy. Then you have to differentiate with respect to tau this, which is also very simple. Okay, because as I said before, the maximum is equal for both of them, and you finally find, solving this equation, you find that the estimator is simply the average of the times. Very simple, very straightforward. I also write to you for you the derivative, but I hope you can do it. Okay, now you can go to the other properties because they are very important. So we can now estimate the average of the ensemble average of our estimator, just to be clear. Sorry. And to do this, we use the usual definition, and we carry out the integration, and we discover that it is tau. So we have now to discover if our estimator is convergent to tau. We'll see in a while. Then for the variance, a similar definition where we have put the distribution around the average value with the usual distribution function, and we get that it is the square of tau. Okay, these are the values with which we have to compare, and now let's see what happens for the average of our estimator. So we have to do the same thing, but instead of using t, we have to input our definition of the estimator, our estimate. So we put inside this, and we discover, very easy to demonstrate by using the property of the average, that it is equal to tau, which means that the likelihood estimator is unbiased, in this case, of course. Then we go with the variance, and we discover that the variance scales with the square root of n, which is a general result, let me say. So depending on the number of the population we use for the estimator, we can get that the spread of the estimator is the original spread of the distribution divided by the square root of the number of measurements, which is expected by now we have also demonstrated.
And here we are near to the end.
Yeah, unfortunately I have not finished. So tomorrow I have to restart from here because I can't.
I don't know if you wanted to do this example, I don't know. Try to.
Yeah, maybe. No, this for sure. I wanted to understand if. Okay, I can stop here. I guess. Va bene. I mean, there is all the part with the covariance, and tomorrow we'll try to be more quick. So, Binet exponential. I mentioned before that the example I gave was done with an unbinned distribution, which means that each occurrence time was available separately, and we built the distribution function for each of them. But in many cases, the events are gathered or collected in histograms. So each histogram gathers n1 and n events. And this is the so-called binned distribution or histogram. Is it possible to apply the likelihood estimator also here? Of course, yes. And it's also very straightforward. We have just to understand what is the distribution function for this histogram. And we have learned that it can be or the multidimensional, or depending on the value of the total number of events, also on a Poisson. For simplicity, we can use the Poisson, which is much easier to write. And so we can write that the distribution for the k value, the k bin of the histogram given tau is given by this probability, where the expected value depends, of course, on the position of the bin. Okay, so it's the integral between the time k minus 1 to the time k of the exponential law, and it is given by this. So in the end, you get a very similar distribution to the one we got from the unbinned, but apart from this term here. So the result is not, of course, the same, and the spatial is not so easy to obtain, but this can be easily obtained by numerical evaluation. Let me say that most experiments are using the likelihood Binet experiment. Many experiments are using the Binet exponential to bin. To be honest, I'm not sure Gerda here is using the Binet fit, because is it also possible that you know exactly where the points are and you use an unbinned estimator to obtain the parameters of the model. But then when you plot it, it's much more straightforward to understand what is the outcome of the measurement by using a histogram. So what usually happens is that you are using an unbinned fit, but you are using a binned spectrum to show it. In any case, I wanted to convince you that also, in case you don't have the information of the single events, you can use binned spectra also for having an estimation. Okay, I exhausted my time, so I think I have to close here.
Thank you very much. Because in fact, your lecture was fantastic. So it wasn't true that you are not an expert. Maybe it's better not to have an expert because you're more nice. So I remember everybody that tomorrow there is the second part, and then there are also other two hands-on sessions on statistics. And now there is, I don't know if there are questions, but there is this session of questions. I remember, Oliviero, that there is again the question that you have received before, written in the chat, if you wanted to read it carefully. And remember that Walter wrote the link for the new session of the questions that is different with respect to the one that we are using this moment. For the rest, I don't know. I ask the other to intervene.
Yeah, the link can also be found on the page of a meeting. So.
Yes. Okay.
Let's move on the other room if people want to ask a question. Even the most trivial ones, don't be scared to ask questions, even basic.
Okay, perfect. Thank you again, Oliviero.
Thanks to you.